Good morning, everyone. I hope you can hear me okay. Thanks for joining in on the mini-symposium on approximate computing in numerical linear algebra. I'm happy to introduce our first speaker, Mantas Mikaitis. He obtained his bachelor's as well as master's from the Manchester University and is now a lecturer in Leeds. And he will talk about the accuracy of mathematical functions in Julia. Mantas, please take it away.
Okay, thank you, Jonas. Can you hear me okay? Okay, so we did this project on Julia. I'm not typically a Julia programmer, but I work in computer arithmetic, so I'm interested in floating point algorithms, floating point theory, accuracy, and things like that. And I have students like Ted Jasper, who was working with me on this project, who also look at these aspects. So in recent, maybe 2-3 years, the computer arithmetic community has showed that you can create correctly rounded elementary functions such as exponentials, logarithms, sine, cosine, quite cheaply for single and double precision. So that wasn't true maybe 10-15 years ago. We didn't have clearly written down algorithms, and we didn't know how to achieve it. But it's now changing, and computer arithmetic is becoming more informed about how to do these things. So various mathematical libraries are converging towards providing correctly rounded mathematical operations. So that means, I will explain what that means in terms of the IEEE standard, but basically that means that for every input you have a unique output. It will not vary between the systems and implementations. So for example, if you take a floating point addition, that's already true for decades. We know very well how to make it correctly rounded, but not for exponentials and logarithms and things like that. Okay, so this was the focus of this work, and we basically wanted to help Julia transition into that correctly rounded phase when it starts doing that. Okay, all of the libraries are starting to do that already. We are seeing that, and once Julia is ready, we wanted to help it do that with this creatively named package, Math Benchmark, which actually just tests the trigonometric functions and exponentials and logarithms in Julia and gives you an easy to understand measure of the accuracy. So I'll give you a short demo first before I start talking about it. So here's the root of my package, and it has a very simple configuration file, config.json. And if we have a look inside right now, I have 2 tests, one for binary 16 mathematical functions, and I'm going to run something called search exhaustive. So that's going to look at all possible inputs for binary 16, because that's very easy to do actually in binary 16. Now for binary 32, I also say exhaustive, but that's going to take a long time, as you will see. That's not going to run very quickly. So this is an easy to configure config file. And to run this software, it's pretty standard. We just say Julia, it's multi-threaded, so it's going to split up the input space of the functions and distribute it across the threads. And it's going to do the testing and combine it to give us a result. So as you can see, what happens here is that binary 16 functions, you can see a list of functions starting with x2, tangent, square root, and so on, are tested very quickly on 12 threads, and you probably have a result already that you can have a look at. But now we are stuck at this step here, which is binary 32 testing, which has about 2 billion tests to do. Okay, so that's going to eventually complete as well, but that shows a difference very easily how big the testing is. And I can have a look at the outputs for the binary 16. That's a simple text file that I provide, and the output looks pretty much like this. It's a list of functions, and the second column is the most important. It's the error in what is called ULP. It's a standard measure of accuracy in computer arithmetic, and to be correctly rounded, you're looking to be below 0.5. Okay, so in this case, we can see that Julia's binary 16 some of the functions are correctly rounded, and some are just above that point. And also you have the input and output for the cases that give us that worst case error. And we also have a number of tests that were run. So in binary 16, it's a relatively small number of tests. Okay, so let's have a look at some background. If we look at 754, which is the standard of floating point arithmetic that's been there for 40 years, it's in fourth revision right now, due to come out in 2029. That defines correct rounding in clause 2.1, and it tells us that it's a method of converting an infinitely precise result to a floating point number as determined by an applicable rounding direction. Okay, so for each rounding direction, you have a different correctly rounded result. Now, clause 9.2 says that conforming operation that conforms to the standard shall return the results correctly rounded for the applicable rounding direction for all operands in its domain. Okay, so it's a quite a strict requirement to be conformant to correctly rounded requirement. Now with addition, division, and square root, it's quite easy, but with exponentials, logarithms, as I said, it's a difficult problem, and we will see why. Now, you have this kind of a problem in the red box. Rounding itself is easy, so you can implement round to nearest quite easily of an exponential function result. You just look at bits and say, I'm gonna go left or right based on the bits that I'm rounding. But it's the approximation that causes a correctly rounded result. You are correctly rounding it with round to nearest to actually end up incorrectly rounded. Okay, so it's the approximation that you're dealing with. That's the hard part of the function. Okay, so these are required operations by IEEE 754. So you have addition, subtraction, multiplication, division, square root, and an FMA. So as I said, these are easy to make correctly rounded. We know how to do it. And that's why they are strictly required. These are building blocks, okay? So the expressions computed, I'm sure everybody knows this, but just in case someone is not an expert in this, if you build complicated expressions like a dot product with multipliers and adders, that's not gonna be correctly rounded. Okay, so it's not gonna have that property of infinitely computing a dot product and then rounding it once to a target precision. So it's gonna be error introduced on every operation. So these are building blocks. Now mathematical functions are only recommended by IEEE 754. Okay, so it recommends these functions on the screen, and the ones that I underlined are the ones that we are testing in this first iteration of the toolbox. Mainly three categories. You have logarithms, you have exponentials, and a lot of trigonometric functions. Single inputs for now. We are looking to do double, two inputs, but that obviously makes the search space really difficult to cover. So we're just focusing on single inputs for now. Okay, so why is correct rounding so difficult? Well, you have rounding breakpoints, and in exponential functions, for example, you don't know which side of the rounding breakpoint you are. Basically, you don't know how precise you have to be in the approximation, in the polynomial, to know which side of the rounding breakpoint you are. Okay, so here's an example. Take the Maclaurin series for e to the power of x, and that is basically saying on every iteration I'm adding a smaller and smaller correction to the approximation. And on second step there I'm showing a result due to Vincent Lefebvre that shows that in B float 16, if you enter that input there to the exponential, you will get this expansion here. Let's see if this works. So you will get this expansion, and this is the correctly rounded result to B float 16. If you apply round to 0 to this exact result, you will have 1, 1 there in the end. But if you do the Maclaurin series just for 8 steps, what happens is that you're just below the rounding breakpoint. So you haven't arrived to the point where the last bit becomes 1, but you're really close there. And if you take another step, it will get you through the rounding breakpoint and then give you a correctly rounded round to 0 result. But if you just do a round to 0 of this approximation at k equals 8, you are obviously not correctly rounded then, because that result is different from that result there. Here's another way to visualize it. So on X, you have the Maclaurin series iterations, and on Y, you have the value. And there I drew a couple of, well, 3 lines. One is the rounding breakpoint. This is the exact function that is a Maclaurin series function that is approaching the breakpoint. And these are the 2 floating point values in B float 16 that you can round to. So you can see this approximation goes closer and closer to the rounding breakpoint. And of course, it steps through it at that point. And round to nearest would go up if you were rounding with round to nearest. But if you did round to nearest before it breaks through there, you would go down. 15 minutes left, or I spent 15 minutes already? Left. Okay, thanks. So this survey paper, published last year in ACM Computing Surveys, really tries to make a point that now is the time to provide correctly rounded trigonometric functions and exponential functions. And these guys have been working on it for about 40 years on the algorithms and the theory. And they give a convincing case that the algorithms are now there to quite cheaply approximate correctly rounded operations. The development time may be costly, but when you actually implement it and prove that it's correctly rounded, the evaluation to the user is not that much more expensive. Okay, so let's look at Julia's. What was the problem we are dealing with in Julia here? So we have mainly 3 floating point formats: binary 16, binary 32, and binary 64. There is like B float as well, and you can include the different formats using different packages. But these are, tell me if I'm wrong, but these are in the base Julia, so I can use them just installing Julia, I can use them directly. So binary 16, and all of these are IEEE 754 formats. Binary 16 is like a narrow range and small precision format. So you have the exponent limitation. Okay, I cannot see that small pointer, so I'll use this pointer instead. So you have quite a narrow exponent limitation for binary 16. And this is the precision in bits. So you have 11 bits for binary 16. This is the smallest subnormal number that you can represent in binary 16. This is the smallest normal number. And normals versus subnormals have different precision properties. And this is the largest positive value we can represent. After this, we go to infinity. And most importantly to us is how many numbers can the format represent. Okay, so this means the upper bound on how many we will have to check in our test of mathematical functions. So you can see for binary 16, it's quite feasible, 63,000, and you saw that the test ran very easily, very quickly. For single precision, it's about 4 billion values that you have to test for the full range between minus infinity and plus infinity. So that's also doable, especially at a high parallel. If you have many cores at a high parallelism, you can do it. I even do it on my laptop in about, I think, 8 hours for the full test. But now for binary 64, that's where the issue is. Obviously, you cannot cover that input space. So for each function, this is the upper bound of how many inputs you would have to try to actually test the function fully. Okay, ULP errors. There's a lot of stuff on the slide. I just made it like a notes. You can have a look offline. But with ULP errors, you can think about it this way. So you may know that the floating point, if you start at 0 and go towards plus and minus infinity, floating point steps between floating point numbers are getting bigger and bigger. The bigger the number is, the larger the step between floating point numbers. It actually doubles on the powers of 2. So we cannot use an absolute error to measure the accuracy, because if your answer is around 1 million, the step between numbers is a particular step. And if your answer is around 0, the step between numbers is much smaller. So we use this ULP error measure. And this is absolute error divided by the step size between the number that you're dealing with and the next number in floating point representation. So our tool has to compute that, and we're using things like next after F and next after in Julia, or use bit level representations to compute it. Now, each function has a different input range where it makes sense. So you not necessarily have to cover the full range of the format between -infinity and +infinity. You can look at specific functions and try to squeeze the range to a particular point where you are just testing where it makes sense. So we derived for each of the function a specific input range for each of the each of the 3 formats where it makes sense to test it. Outside that range, it doesn't make sense, so it makes it more efficient if we have those input ranges. So that means the function is defined in that input range, A, B. It doesn't overflow. So if you're getting infinities or -infinities, that probably is an easy case to solve, so we are not testing that at present. And it also does not converge to a constant output value. For example, when you're raising e to the large negative power, at some point you're always staying at 0 there, so we are not checking past certain negative values. If you look at the source code, functions.jl contains an input range for each function and each format. So we had to hard code those. And this is an example for binary 32. You can see some of the functions have nice input ranges. So for example, ACOS has -1 to 1, and that's a nice input range to find out. But some of other functions like the exponential has this quite a complicated input range, which we found by reasoning about what will happen if I go to, for example, -104, which gets me, which makes the answer underflow to 0. Okay, so if you go lower and lower than -104, you're always staying at 0. So at that point, you don't actually have to look at the elementary function result. Similar for all the rest of the cases. Now, for some of these functions, I have to look at the full range. So for example, for cos pi, I have to look at the full range between the -fmax and fmax, which are the maximum representable numbers in the floating point system. Okay, so previous work, some previous results. The key paper is by Gladman and his colleagues. This is a kind of an archive paper that we keep updating every few months, testing more and more libraries as we are converging towards correctly rounded implementations. So on the y-axis, you have all the libraries that we keep testing and their versions. And on the x-axis, you have the functions, and this is just half of the table. I couldn't fit the whole thing, but you should get hold of the paper if you're interested. So you can see there are 2 libraries that are mainly correctly rounded. GNU libc, which has a lot of functions correctly rounded, and some of them are still converging towards that. And then LLVM, and this is for single precision, binary 32. LLVM is fully correctly rounded, except of some functions that it actually doesn't even have. That's where the empty space is. And then all of the rest of the libraries have errors between just above 0.5 ULPs, so slightly above in correct rounding, and some massive errors in some of the cases where there's probably a bug or something. But in general, the collection of mathematical libraries that you have available are slowly converging towards providing correctly rounded results. And LLVM is showing that we already did it. Now, for double precision, the results are similar. except that LLVM has one case, a ton function, which has one ULP of error. So that means the worst case is one step away rather than half a step away. So I imagine we're still working on that one. But the results are similar for single and double, which proves that double is not more difficult in some respects than single precision. Okay, so how should we cover this massive input space of double precision that we have? What we did is we focused on performance, and we asked the user to specify how long do they want to run per function. And we approximately measure the time it takes to evaluate this function. So that's t in the formula is there. And it's a very rough approximation because it depends on what the CPU is currently doing, some throttling and things like that. If the user says seconds, then the input space coverage will be very coarse. It will go through massive steps through the input space. But if they say hours or days, then we will take more and more samples in that input space and cover more percentage of it. And if they say exhaustive, obviously the idea is to go at a step size of 1, and you're covering the full input space of the format. So here's an example of how the config.json looks in the repository. We placed 3 tests there, binary 16 with exhaustive search strategy, binary 32 with also exhaustive search strategy, and binary 64 with hours search strategy. And actually, when you say binary 64 hours, the expectation is it takes 24 hours because we have 24 functions right now, but it takes about twice that because the benchmarking that we use is actually currently not very accurate. Something changes as the test is running, so it takes much longer. It's a very rough approximation. And then you run the test with just Julia and specifying how many threads you want to use. Now you also have some options for rounding and fast math. Fast math works right now, but we found that there is no effect in Julia. And you can tell me if I did something wrong there. But fast math doesn't affect the accuracy of these mathematical functions. Now the rounding is a future support, because right now there is no concept of rounding for something like an exponential function in Julia. Ideally, you would have x round to nearest, x round to 0, round up and round down, and correctly rounded for each. So that's a feature for when it comes up later. Okay, so results. I run the binary 16 and binary 32 tests on the MacBook, and it takes, I don't know, no more than 1 day to do binary 32 tests on 12 cores. Now, binary 64, I run them on a 168-core AMD EPYC CPU. And unfortunately, I don't have results of Julia 1.12.6 because we are still running. I tried to deliver them for the conference, but we are still running. I have results for 1.11.6, which is about 1 year old, I think. That's when we wrote the first version of the paper. And that takes about 2 days of runtime to do for the hours search strategy, when you say hours. Okay, so binary 16, as we saw, Julia's mathematical functions are pretty much very close to correctly rounded. Some of them are just a little bit above, so it just needs looking into each of them and see what is going on and what would be the way to put them into correct rounding. It's also possible, somebody can tell me, but it's also possible that a binary 64 or 32 result is simply rounded to binary 16 result, which then makes the fixing of these, the job is to fix the other ones, actually, and just do the correct rounding. Okay, so for binary 32, the errors are between 0.5 ULPs and 2.41 ULPs, okay? So very close to correct rounding. Of course, cost H needs looking into, but things like square root and CBRT are already correctly rounded, and the others are very close as well. So this is exhaustive. Both of these were exhaustive. That gives us a worst case error. But then for a double precision, we only have a known worst case error. The coverage space is very small. Okay, you have 10 to the power of 18 or 19 inputs to try. On the right side, you can see how much we actually managed to do in 2 days. So it's about 20 to 30 billion per function. It's a very small percentage-wise coverage of the input space. But still, it gives us a result that's quite similar to single precision. So you have square root still correctly rounded, but then CBRT is 0.66 ULPs, and then all the rest I didn't find much surprises compared to single precision. And these compare very well to Zimmermann's results, Gladman and Zimmermann's results. Okay, so conclusions. We have developed this easy-to-run test suite. Hopefully that makes Julia transition in the next, I don't know, 3 to 10 years to correctly rounded operations for mathematical functions. We find that most functions are close to being correctly rounded. There are no massive surprises, at least for the tests we run. Although we have to be mindful that the test coverage for double precision is really small, so I need to run it on much bigger, for a much bigger time scale or bigger parallelism. Future work is bivariate functions where you have 2 inputs. So, for example, the power function we haven't tried, x to the power of y. Different search strategies. Instead of fixed step size, we should maybe look at different ranges of each of the function, and of course, bigger proportion of the input space. Now, what should Julia do? I think, in my opinion, I'm not obviously in this community, but in my opinion, I would make fast math option a switch for correctly rounded mathematical functions. And if it's on, we should get the state that we're currently getting, or even looser approximations. So you could go to thousands of OOPs, for example, if you really want speed. But then if fast math is switched off, the user, I think, should get correctly rounded result, because we are now possible to do. Okay, and we have this preprint that is quite old now, 1 year old, but there is a revision coming next week. Okay, and I think that's it.
Thanks, Pantas. Do we have questions from the audience?
Would you imagine, instead of exhaustive search, to use a kind of Doha search for the worst case, as a region-bound approach, for instance, and actually it is easy to detect the wrong cases, probably. This is not foolproof, but
yeah.
it's an approach.
So for binary 16 and 32, exhaustive is the only way, because it's fast. It's doable. For double precision, I agree that we need to look for more sophisticated strategies. Right now, we are stepping in fixed step, but what you suggest is more somehow targeted global search, yeah. So this is something we want to do, yes. But the software is there. It's easy to incorporate new ways to cover the input space. So we're interested to do it. I think there was one there. Yeah.
In Julia, we're in a different space kind of than C or places like so in C and many of the compiled languages, you have a different libc per OS, which makes it very necessary to use correctly rounded functions in order to get reproducible results across architectures.
Mm-hmm.
In a system like Julia, where we have the same implementation for all architectures, is there a difference that matters between correctly rounded and like 0.55?
If you transition languages, for example, you will want to expect Julia to produce the same result at granular operations level. At least I would. And then if you don't have correct rounding, any prior analysis doesn't apply, because correct rounding bounds the maximum error. So if somebody did analysis of the application but then run it in Julia, none of the analysis will apply if it's not correctly rounded. So there is benefit, yeah.
Right, unfortunately, we are running out of time. I have to defer the questions for the coffee break.
Okay, thank you.
Thanks again, Mantas. And he will talk about the topic I'll be able to read in a second.
Oh, sorry, I'm trying to. Okay.
Structured iterative approximations in numerical linear algebra. Thanks for being here, Nicola, and the panel is all yours.
Thank you. I just need to, 1 sec, display, mirror. Mirror. Apply. Okay. Okay, hello everyone. So I would like to talk about a couple of problems of interest that we have where I work, and these are canonical problems of linear algebra. So first, this is approximate linear solves, where we're given a consistent linear system, and approximate inversion of matrices as a means to produce a preconditioner and be used for more efficient iterative linear solves. And lowering that approximation, which here we consider for a D-way array, but works also for matrices where basically data is approximated with a sum of other products of Laurent factors. And we are interested in the vanilla variants of these problems, but also in the case where the main iterate is structured, that is, for example, sparse, definite, symmetric, non-negative, or else. And we start with sparse approximate inverses, and we look particularly here in the case of right approximate inverses. So we have our matrix of inter-x A, and we say that M is a good right approximate inverse of A if A times M is approximately equal to the identity matrix. And of importance to us is that we are able to efficiently apply that matrix X. So for any given vector X, we can compute M times X efficiently. That's, in a nutshell, the properties of a good sparse approximate inverse to be used in the context of linear solve for preconditioning. And with right approximate inverse, say rat preconditioning. And so that is, instead of solving for x in ax equals b, we solve for u in a times m times u equals b. And associated solver implementations will have an application basically of the preconditioner. Every time you have a preconditioner of the matrix, you solve for u, and once you have it, your solution of the original system is m times u. And this is interesting because the convergence of these iterative behaviors depend on the spectral properties of that AM matrix. So when A is sparse, although the inverse is generally dense, it sometimes contains sufficiently many low magnitude components so that discarding them can allow to do a good sparse approximate inverse, which can mean different things in different sense, but particularly for the case of preconditioning. One thing that we consider is the best SPAI for a prescribed sparsity pattern. So if you have a prescribed sparsity pattern, you can obtain a best sparse approximate inverse for that pattern by looking at the square of the Frobenius norm of the residual of the iterate, which embarrassingly decomposes into independent least square, sparse least square solves. But in general, we do not know the sparsity pattern of M ahead of time, which is best to achieve a good SPAI with preconditional properties. So standard choices are either to take A or the sparsity pattern of A square or acute or other low degree monomials like this. But what we see is that even those choices can fail to yield good SPAIs. So for example, here you have a matrix from is that pseudo-sparse matrix collection? Yeah. And okay, that matrix is MCS 04515. And we consider here best SPAIs that we just mentioned with different sparsity patterns specified here. So either we use the diagonal matrix or you use the sparsity pattern of A square, and so on. And these are spectra of the best SPAI constructed for these associated sparsity patterns. At the very bottom, you have the spectrum of the inverse of the matrix MCS 04515. Which is positive definite, so the whole part of the spectrum is positive. If you construct the best diagonal approximation, that approximation is also SPD, which is not surprising, as it is the Jacobi preconditioner of a SPD matrix. However, if you start building best SPAIs for sparsity patterns of higher degrees, then you get all these negative eigenvalues. So that your SPAIs, even though it's a best SPAI, it's not qualitatively matching what you want from your iteration, from your approximation, because as you perhaps know, if you want to solve linear systems with that matrix, you will use CGE, and if your preconditioner or SPAI is not SPD, then you will get not so nice behaviors with your vector iteration. Sorry for that. Yeah. And on the right were the sparsity patterns corresponding. Right? So there exist alternative strategies that iterate from one sparsity pattern to another, gradually building a better SPAI, and we call these sparse matrix iterations. And the starting point of thinking of them is perhaps the objective function that we seek to minimize when we form these SPAIs. So that is the square norm of the square of the Frobenius norm of the residual here, which has for a gradient something aligned with, I think it's -2 times A transpose times the residual. And a first method that is known for that purpose is the Newton-Schulz iteration, where basically they consider a scalar inversion problem, which they solve through Newton-Raphson iteration, and then what they do, they take the iterate, which are scalar for that procedure, and they replace them by matrix iterates. And that makes the for the iteration of the Newton. You also have a steepest descent, where what you do is that at every given iterate m sub I, you step one step away along the gradient to find the minimizing SPI in that one-dimensional affine subspace, and that procedure is equivalently stated by these orthogonality properties here. Alternatively to Newton-Schulz and steepest descent, instead of stepping away in the direction of the gradient, like this here, we can step away along the residual. And that method then becomes the minimal residual method. Okay? Yeah. So one thing to keep in mind is that these iterations are implemented with sparse data structures and associated sparse linear algebraic kernels. And the sparsity pattern of the matrix iterate varies from one iterate to another. And in a sense, we are learning sparsity patterns for SPAs. However, even with these methods that we've presented here, the three methods, Newton-Schulz, steepest descent, and minimal residual, we still have difficulties at times at producing good SPAIs. And so for that, we're in a working paper that we put online last year with Professor Ernst, we introduced a locally enriched variant of minimal residual that we call locally LOMR. And the difference is that instead of stepping away in a one-dimensional space, here we preserve search direction history and we form the best approximation in this 2D affine space. Okay? And then we form the linear combination of these two as the new search direction. Which we keep for them, and so on. Yeah, and so that's what we call the locally optimal variant of minimal residual. And one last method that we consider also that we advocate the use of is simply CG. So CG with matrix iterates and with inner products consider as Frobenius inner products as a means to produce your SPAI. So these are experiments where we do not drop zeros. So in practice, when you compute an SPAI, you want to contain the number of non-zero components you build. As you grow through iterations, it can grow uncontrollably to the point that your matrix is essentially dense. And to alleviate this, what we do in later cases is that we introduce a dropping strategy, of which we tried several actually. And perhaps the simplest is what we call hard thresholding, namely just get rid of the components with the smallest magnitude, so as you keep your cap on density. But these results here on this slide do not have yet the dropping strategy, and we just want to see nicely without dropping strategy what happens with these methods. And I think there are two things. First, the steepest descent and minimal residual converge like extremely slow, if at all. But that's not too surprising, at least for minimal residual. And the two other methods that here do converge are the CG, so matrix iterate CG with Frobenius inner product, and LOMR, which is the method we suggested. The difference being that CG is subjected to spurious oscillations, which are proper to its sensitivity to the spectrum of A. Whereas LOMR is monotone, decreasing, and can serve as we can say, a lower envelope of the CG behavior and the MR behavior. But this is behaviors without dropping. And now we have experiments with dropping. So we say, I think it's 3%. Once the number of non-zeros reaches 3%, then we start acting, we get rid of the smallest component. And in the meantime, we deploy the matrix iteration that we just mentioned. And here, this slide has two plots. The first plot is the Frobenius norm of the matrix residual for the computation of the SPAI, okay? And we see the three methods that we've mentioned with the sparsity patterns that we obtain after 100 iterations. And the bottom part is the PCG iteration conducted with these matrices as preconditioners. Okay? First thing that we can see is that the level of residual norm that we can achieve varies widely from one method to another. And also you can see that here the reference behavior is PCG Jacobi in red. And basically none of these methods that we try manage to do significantly better than Jacobi, or if at all. This one just for small backward errors start to do better. But so there are cases for which it's difficult to build a good SPI in the sense that it serves as a good preconditioner. But there are cases where it's way more feasible. So you can see now the strong gap between the PCG behavior with Jacobi preconditioner versus the SPAI as preconditioners. And here you see one, again, an instance of this spurious behavior of CG before it comes back down to eventually produce an SPAI that performs as well as LOMR in terms of preconditioning. There are cases for which all methods work the same. Here, going from 2 iterations per solve to from 10 to 2 iterations per solve, irrespective of the method. And there are cases where we understand a little bit less what happens, like here. So we see that the LOPMR goes down the most in terms of residual norm of the matrix residual, but it fails to accelerate the convergence of PCG when used as a preconditioner. Whereas MR, which is seemingly not as optimal, is the only preconditioner that accelerate convergence here. And this is interesting to notice that this is something that happens as the dropping strategy kicks in, and the SPI that we construct with MR here, in this case, are structurally different from the others with LOMR and PCG. Yeah. Okay, so there was a bunch of methods that we presented, and we realized that there is no clear conclusion as to which one is better than the others and so on for every situation. So we tried to make everything available on a repo. And as of yesterday, I tried to do the registration online with the bot. It did not go all the way through, but the repo is public, it's open, and I will be doing the necessary for the registration as soon as I can. Yeah. And what else is going on? Well, we have other efforts going on with students, and they are aimed at alleviating the monstrous cost associated with performing these matrix iterations. And there are 2 ways that we are considering. First is mixed precision, that is, do as many costly parts of matrix iterations as possible in lower precision arithmetic, to which we can say from preliminary results that it seems to work not too bad to do the matrix iteration in low precision, but do the best SPAI computation with the so obtained sparsity pattern in higher precision. Yeah, and we're also considering self-preconditioning variants where we have an outer and inner iteration, and basically you are utilizing your SPAI, your currently constructed SPAI, as a preconditioner to your improvement of the very SPAI. So it's self-preconditioned variant, and it is more interesting for parallelization. And yeah. And do I still have time? Or? Yeah? Okay. And the last part is about low-rank array approximation. So similarly as for the matrix inverse approximation, we can take from starting point an objective function we seek to minimize. So here I dropped the f, but we can think of this as the two norm of the Frobenius, the square of the Frobenius norm of the representation error between the observed data and the low-rank approximation formed by addition of other products. Okay, and we can construct short recurrence iterations using, once again, the gradient of that objective function with respect to each low-rank factor, bunch of low-rank factors. And we can also introduce Petrov-Galerkin gradient descent, where the low-rank factors are obtained by stepping away along a gradient once again, and we need to complete that with orthogonality constraints to close our system. And in 2D, so for the matrix case, this gives us these orthogonality constraint of the residual with respect to the right low-rank factor and the orthogonal the transpose of the residual with respect to the left low-rank factor. And also, similarly as we can do in SPAIs, we can also have a locally optimal variant of this Petrov-Galerkin gradient descent. And here this is a test, so we say we have a fixed amount of time, and we try to compute a low-rank approximation using either the Petrov-Galerkin gradient descent on the left or the locally optimal variant on the right. And you can see that the locally optimal variant makes more progress towards satisfactory low-rank approximations. And we're currently investigating applications of these locally optimal variants for structured low-rank approximation. That's it.
Thanks, Nicolas. Do we have questions from the audience? Let's try the microphone once more.
For the sparse approximate inverses that you were showing before, oh yeah, when you were looking at some matrices and your sparse approximate inverse would work and it wouldn't work in other cases.
Yeah.
Do you know about like the eigenvalues of that matrix or like the condition number of those matrices and if that was significantly different when you were approximating it?
Yes, I have that information. So all the matrices here were SPD because we were motivated by the fact that when we try to build SPAIs for matrices that are SPD, what we get is not SPD. So we started by focusing on SPD matrices, and even though we don't explicitly try to enforce definiteness, we try to have a better method that goes towards that. So yeah, point short, all the matrices were SPD. They were different different conditioning number indeed, but there was no we were not able to extract any strong result as to how the spectral properties of the matrix impact the convergence. Okay.
So that doesn't seem to be what was causing the difference.
Oh, it could be, but not in the way that we were able to reveal at least.
Okay.
Yeah.
Cool.
Yeah. I mean, there are results that apply for CG. So all the results on convergence that you have for CG can be applied similarly. So for CG, yes, you can have more information by exploiting what exists already to characterize the CG convergence for the CG applied here with matrix iterates. But for MR, we just have like a rate of convergence which depends on the indeed on the eigenvalues, but this works for MR and this works a fortiori for LOMR, but it's not really revealing of the behavior. Yeah.
How expensive in terms of runtime is it to compute the SPAs?
So it depends on the size, but even for, so I did the test cases on what I call small matrices, which are up to, I don't know, like 4,000 to 5,000 degrees of freedom, so that I can compute everything about it and exhaustively characterize what I'm doing. And I had medium-sized matrices that were 20 to 30,000 degrees of freedom. And so I would say a few minutes without dropping non-zeros for the smaller one, but definitely significantly more for the larger one. And the larger ones, you cannot really think of deploying them without the dropping strategies. But even then, because you operate on the data structure, there is a lot of data movement and so on. It's not optimal to implement efficiently, let's say. So there is a cost, yeah, a significant cost, yeah.
Okay, do we have more questions? Yeah.
Hi, nice talk. I guess in the same vein as like the spectral properties of the matrices, maybe looking at the pseudospectral properties of the matrices.
This is not something I investigated.
Yeah, I mean maybe that could be like useful
Sure,
to kind of characterize like yeah, if you have like norm greater than 1 or something like this, the sparsity pattern is not enough. Maybe could be more descriptive.
Okay. Thank you for that.
Okay, if we don't have more questions, then let's thank Nicola again. And now we do a coffee break and continue at 11:15. See you then. Welcome back, everyone, to the second half or second part of our mini symposium on approximate computing and numerical linear algebra. It's a pleasure to me to introduce Andreas Varga to you, who has obtained his PhD in control theory and systems and control theory in Hungary a very, very long time ago.
Romania.
Sorry?
Romania.
From Romania, I'm sorry, not Hungary. And then he went on to a Humboldt stipend in Bochum and continued his career or finished his career then as a senior scientist at the DLR, the German Aerospace Institute in Pfaffenhofen, close to Munich. And now he's retired. And so it's a special pleasure to me to have got you back from retirement for a talk at this conference. Andreas, please.
Okay. Jonas, thank you very much for your invitation, and this was a good opportunity for me to revise this package, to improve it a little bit even more. So just to not, this is an outline of my presentation, a short introduction, some matrix equations which are covered by this package, and some general ideas about the solution methods. Then I will tell the story of the software development for this package. And finally, the main part are performance issues and genericity aspects, which are discussed in some details and some conclusions. So let's start with the introduction. The main goal of this package, I have a control background, so it was just to provide high-performance numerical software to solve some classes of linear and quadratic matrix equations which were relevant for control application. The function of this package covers the solution of Lyapunov, Sylvester, Riccati equation, also some special cases, so-called Lyapunov-like, Sylvester-like, or linear equation with many terms, more than two, then evaluation of norm, condition numbers, separation for Lyapunov and Sylvester equation. The data which are covered are, of course, real and complex. There's the whole range of IEEE single and double precision, floating point numbers, and also extended precision floating point representation. Okay, so these are an overview of the equation. So the most classic equation is the Lyapunov equation, which has a continuous form and a discrete form. This is also a transposed version of this equation. There exists the generalized Lyapunov matrix equation, where we have additionally here an E matrix, both also in continuous and discrete form. A little bit more general are the Sylvester matrix equation, which these have also two forms. The continuous one, which is this, which play a big role in many linear algebra computation, in eigenvalue decomposition, and the discrete time form. And of course, the generalized Sylvester matrix equation and extension to a system. Okay. Also, Riccati matrix equations are covered. I just show you this slide just to have an idea what can be solved. This is not relevant for my talk. So I continue with a very short overview of the solution methods. So, and I will consider just an example, the real Lyapunov matrix equation, which has this form. The matrices are A square, C square, and X is the solution which we would like to determine. Necessary and sufficient condition for the existence of a unique solution is that the A matrix has no eigenvalues alpha and beta such that the sum is zero. Interestingly, if the C matrix is symmetric, then X is also symmetric. So there is an analytic solution which you can write down with the help of this vector mapping, where you map the columns of the matrix, you stack them one below the others, and using the Kronecker product representation, it is possible to write the solution in this analytic form. Certainly, you can use this also to compute the solution, but actually it is not very practical for large values of n because of the computational complexity of n to 6. So this is the reason for which transformation methods, which are very, very common in numerical linear algebra, are used also in this case. So we transform the problem, with the help of the orthogonal reduction of A matrix to a real Schur form, such that we obtain a reduced equation. I am not, this is a Sylvester. Okay, sorry. So we obtain a reduced Lyapunov equation, which A tilde is in a real Schur form, and which can be solved efficiently using special methods. For instance, the well-known Bartlett-Stewart algorithm. The solution is this, and what is interesting for this that besides the computational effort, which is acceptable for all linear algebra computation, we have numerical stability guaranteed, and we can exploit the structure. So if C is symmetric, C tilde is also symmetric, X tilde is symmetric, and the solution is symmetric. So only the upper triangular part needs to be computed in principle. Something similar for the Sylvester matrix equation. This equation involves two matrices A and B, whose eigenvalues should not add to 0. This is a necessary and sufficient condition. And once again, we have an analytic solution with expressed with Kronecker products. The computational effort is once again large for large products of M or N, and this is not a practical one. So once again, we use the same paradigm for a lot of linear algebra computation to reduce the problem to simpler one. In this case, we use two matrices to compute the real Schur form of A and of B. We solve this reduced equation, and we get the final solution in this way. This algorithm is acceptable as a computational effort. Numerical stability is guaranteed, and what happens if M and N are large? It is possible to enhance the algorithmic efficiency using blocking-based variant. Okay, of this I will talk later. So I will skip this slide. The Riccati equation is important in this discussion only for the last aspect, the role of scaling to enhance accuracy. But okay, I don't insist more on that. Now, the story of the software development. So the situation in 2018 in the field of matrix equation. So there were a complete set of solvers which were available in the Slycott Fortran library. And there were a lot of wrappers which were based on this in MATLAB and even in Octave and Scilab, which were free. There was also a function even in Julia, which relied on the Sylvester equation solvers from LAPACK. My initial goal, when I started implementing this package, it was first to learn Julia. I had no idea, but I thought it was an interesting language. Some features were more pleasant than in MATLAB, so this was one of my goals. The second, I intended to cover both single and double precision and to have somehow the same performance as the slide code routines, which were the standard at that time. So I started the implementation. Some initial decisions partly were not good. They were later revised. For one which was accepted is to use different names for different Lyapunov solvers, so the continuous and the discrete one. Use different name for the standard generalized equation. This was wrong. So this can be avoided using dynamic dispatch. Also, to treat explicitly the transpose case without forming the transpose matrices. This was done with flags. This can be also done using dynamic dispatch. So, and to cover both single and double precision for real and complex data. The first version was implemented with Julia version 1.1 and included solver for Lyapunov and Riccati equation, some prototype solvers for Sylvester equation, and the first good news, my implementation, LiapC, outperformed Julia's own Liap. So this was the good news. And also comparing with the MATLAB, the complex Lyapunov solver were faster somewhere as the MATLAB, which were based on slide code. Okay, so here toward the version 1.0. Okay, I will go faster. I added the new solvers for Sylvester and Sylvester systems, simplified interfaces for Lyapunov solvers, transposed equation. So the planned functionality was achieved in release 0.8, and the release 1.0 was delivered in November 2019. And actually, this was my goal to memorize. Then I received some critics that some implementations are not quite performant. So I started to refine them. So I achieved improvement, 50 to 100 speed boost by reducing just the allocation burden. And then it followed with version 2, including linear maps as a helper package, then adding some generic solvers, then solvers for special equation, Lyapunov-like and Sylvester-like, then iterative solvers, and then adding 8 scaling options to regard to equation. MATLAB has just one. So it is just for comparison. And in August 2026, so 1 week last week, I produced the release 2.6.3 with a whole bunch of recursive blocking-based solvers for Lyapunov and Sylvester equations. So let's go to the performance issues. So how it is possible to improve the performance? So the main way is to reduce the storage allocation. This is a typical aspect in Julia, then exploiting the structure, and finally, this is what I did in the last 2 months, trying to optimize the usage of cache. And this was my desktop PC, which I used for test. This is not very fast, but also not very slow. So 2.9 gigahertz. These are the values of the cache. It is running under Windows with the Julia version 1.12 with the MKL library, similarly as MATLAB 2024B, which I use for comparisons. So to reduce the storage allocation, standard tricks in Julia are to achieve zero allocation inner loops, to employ views instead of slicing, use mutating and in-place functions, pre-allocate buffer. So these are standard techniques which are common to Fortran programming, so it was not very difficult to understand. And this is one of the first things which I achieved. So the version 0.2 of LIAP, see, which was a prototype implementation, and this is a refined version in version 1.2. Okay, so this was 2 times faster now, just using these allocation reduction tricks. The next issue is to exploit structure, for instance, the symmetry. So the symmetry can be exploited. So if C is symmetric, X is symmetric, and okay, the intermediate values are also symmetric. So we have to compute only roughly the half of the elements. And we can also efficiently compute this product. So overall, we got this figure. So the Julia's own LIAP does not exploit symmetry. And this can be seen also in the implementation of matrix equation. So this is almost 3 times faster than the Julia's implementation. Other structure element can be also exploited as if A is symmetric. So after the reduction, the sure form is actually diagonal, so we can use explicit formula. And this is also a huge improvement in the speed. And finally, if it happens that A is diagonal, then the transformation matrix is just the identity matrix. And so once again, we can use explicit formulas, and here the gain is even more substantial. So you can see this is 1.27 seconds from the best version, which I had, to 0.007. And these are matrices of order 4,000. Okay. Lastly, the last performance improvement is related to using the cache memory of the computer. And actually, there are so-called cache-aware algorithms which try to minimize the number of cache misses and maximize the number of cache hits, because these are the issue which, at a large dimension, represents the break of the computation. So such algorithms are already in LAPAC. So the recent implementation of Sylvester solvers use such an algorithm which is based on blocking, and it is splitting the large matrices into smaller blocks, but of fixed size. And what I employed in my new implementation was a recursive matrix blocking, so dividing recursively the large matrices into smaller blocks until they fit into the cache. And to implement such a solver, for instance, for the Lyapunov equation, this means, okay, we have a least block size. If the matrices are below this size, then we use a standard algorithm. If not, we split these matrices in blocks, and we solve recursively these equations, which are now on the blocks. This is once again a plenty Lyapunov equation of reduced form. This is one which is updated. Updating can be done with the general matrix multiplication very fast. And the last updating is a symmetric rank to K update, which can be done also very fast. And if this equation fits in the cache, then they are solved with the standard method. If not, they are once again recursively reduced. Okay, what can be achieved with this? This is simply, I'm comparing single thread and A-thread computation. And you see, it's, with one thread, the computational time of the standard algorithm which I had was 86 seconds, with the new one 29. So this is a net gain in speed. With 8 threads, the times are even better, 77 seconds to 17 seconds. So the achieved speed boosts are about 3 times in a single thread and more than 4 times in a thread case. When I compare with the MATLAB, these are the figures for MATLAB, and actually the speedups achieved by Julia and MATLAB are almost the same, but in all cases, Julia is better. So these are the times from Julia, and these are the times from MATLAB. This is one of the last tests which I performed using a generalized Lyapunov equation. So here the times are much larger. The MATLAB times are even larger. So what I achieved is a speed boost of 1.73. And when I compare with MATLAB, so a very interesting fact. So the MATLAB with 8 threads is 2 times slower than Julia with 1 thread. So this is a very good result, in my opinion. Okay, now let's go to the genericity aspects. These are the floating point precision or arithmetic which are in Julia base. There's hardware single, hardware double, and big float. These are provided in Julia. But there exist also packages which implement different kind of extended floating point precision. So this is double-double, multi-limp, through IEEE 128-bit watt precision. These are the tricks which you need to use to make a code generic. I will just discuss one. So avoid concrete types in function signature, or use abstract matrices. One important is the availability of tools to compute singular value decompositions and Schur decompositions. And these are provided in these generic linear algebra packages and in generic Schur packages. And I needed to implement some native Julia software for solving some reduced equation too. Here are some results. I implemented a blocking-based solver for Lyapunov equation just to see what happens. And here are the results for matrices of dimension 500. As expected, the float 32 and 64 achieve the expected speedups. But for the others, there is practically no speedup at all. So this led me to decide that I will not implement blocking-based solvers, at least not in this moment, for non-BLAS float type data. So just go to conclusion. So I consider this package has a state-of-the-art performance, which is a cache-oblivious Lyapunov and Silvester equation solvers, which are based on recursive blocking techniques. And this implementation currently outperforms all existing free and commercial alternatives. Covering so a wide range of floating points has a very good flexibility. What I not discussed is using the scaling techniques to enhance numerical robustness and accuracy, or pushing further the dimension limits using iterative solvers. There exists also extension, so just is a periodic matrix equation package which provides solver for periodic Lyapunov-Sylvester and Riccati differential and difference solver. Finally, I would like to acknowledge the collaboration with the whole Julia community, with special thanks to Daniel Karaj, Ralf Schmidt, and Andreas Noack, which provided these very useful and very nice packages, and which complete the set of what I needed for implementing the generic solvers. Thank you very much.
Thank you, Andreas. Do we have questions from the audience?
Hi, thanks. Very nice talk. I had one question on the generic, higher precision types. At least when I was developing my package, I noticed that when transitioning to something like a GPU, there's a lot more headroom for these types to take advantage of any latency-bound computations. Have you looked at maybe trying to accelerate using a GPU? These kind of.
No, simply no. That's it.
Do you think it might help or?
No. Okay. I had no opportunity. I am still working to add some solvers, and but this could be an idea to have a look on this aspect. No, so until now it was not.
Maybe I can give some feedback on that. A colleague of mine, Martin Köhler, has implemented the MEPAC library, written in Fortran with some StarPU scheduling behind. He also implements a similar blocking strategy as we just saw, but where the sub-blocks are then benchmark-based, scheduled onto either GPUs or CPUs, and therefore you can saturate even a multi-GPU system and get crazy large speed-ups there. Downside is, being Fortran and some other big libraries, it's not that easy to build. I think it's just IEEE double and single.
So just a quick curiosity of mine. I've seen on the slides you use the time macro to time your solution time. Have you tried using benchmark tools or something like that?
Yeah, certainly. But for 4,000 dimensions, benchmark tools, it takes a lot of time. So this is why I executed several times the times and put the final figures here. So these are okay. So no compilation is involved. So okay.
So if there are no more questions, then let's thank Andreas again. Okay, so hello again, this time from a different perspective. The next talk is by myself. I'm Jonas Schulze. I learned programming back in high school in coding for these Lego RTX RCX bricks that you can see on the right, some robots that follow some black lines and try to drive around obstacles and such. And actually, the first languages I've learned were some dialect of C and then Robolab, which looks like LabVIEW. And I don't recall which order it was, but already very early on, I came to enjoy compiled languages. So this is always the perspective I have on Julia as well. Can't help it. My first encounter with Julia was in 2018 with the 1.0 release, where I had to give a seminar talk on Julia for scientific computing. And after it, I talked myself into a research assistant position at our local Max Planck Institute. My task there was to implement a parallel in time scheme to solve a differential Riccati equation that we just saw, the generalized differential Riccati equation with a lowering solution, so the large case. And that means we are not interested in solution objects that are dense matrices, but are given by some factorization. And for a parallel in time scheme, you have to do some networking, but the amount of data to be sent over the network is not evenly distributed. Let's put it that way. So they tried to implement it in Julia 04, had a really hard time, and I suggested to just try it again with the 1.0 release. And that eventually turned into my master's thesis, and I created two separate packages, of which the Parareal package and the DRE package I will present you today. And during the process, I already discovered some of the maybe lesser used aspects or edge cases of the standard library. And one issue that took me very long to create was on the interplay of the base threads library and the distributed package, which when you're using remote channels, just crash or hang on you. And that was actually a very long-standing issue. I think it was not even closed in 1.6. I think it only got closed or actually done in Julia 1.8, but now it should be much, much easier. Unfortunately, I've moved away from distributed computing and only focus on a single machine. So I'd like to tell you now what happened since in the land of DRE-JL. And by now, I'm a PhD student at that same Max Planck Institute. So what's the Riccati equation? I already had a great overview on the many matrix equations there are. I'd like to give you a maybe less math-heavy focus on Riccati control 101 and how to actually get to such a Riccati equation. Many problems in applications engineering can be linearized and written in the so-called state space system. Means I have a vector x, small x of states that follow an ordinary differential equations where I have some square matrix E and A. E we assume to be regular, so its inverse exists. We don't have some algebraic effects going on. This is purely differential here. We can affect our states x with some controls u, of which there are only few, but we are not able to observe the whole system. We can only observe or measure a subset of the states or a linearly derived quantity y, the output of our system. And many systems can be written in this EABC form or EABCD if you have some feed through that u also affects the output, but we don't assume that to be the case here. And this is the bread and butter of many modeling tools, and we can of course derive other problems from it. One of which is the so-called linear quadratic regulator. It's named that way because the dynamics are linear and the cost function on top is quadratic, and it's trying to steer our outputs of the system y close to a desired trajectory y hat. And we do that on a time interval t0 to tf, to the final time, and employ some cost where during the time interval we deviate from our desired trajectory or use some expensive controls to get there. And at the final time we also want to be close to our trajectory. And that we do with some simple matrix-induced norms. So this norm in the middle, for example, just reads U transpose times R times U. And typically these Q, R, and S matrices are supposed to be positive definite. And the funny observation is, for such a system, we can actually describe the optimal control by means of a so-called feedback matrix. And the feedback matrix K is derived from a capital X, a square operator, linear operator X, that actually solves such a differential Riccardi equation we just saw in the past talk. So what does that beast look like with some fancy squares? I try to keep mathematical notation as low as possible. I think the math-heavy slides are over now. So we have some generalized form. So we multiply our solution object from the left and the right with our E matrix again. Then we have some lowering constant term. We have these linear terms in X, and we have a rather simple quadratic term where the inner coefficient here, B times B transpose, is also again low rank. And then we have a constraint at the final time value. So actually, this is a differential equation that's supposed to be solved reverse in time. And when we do that with a, for example, first order Rosenbrock scheme, the quadratic equation becomes a linear one, and therefore we have to solve some algebraic Lyapunov equation every step. But the E matrix is the same. The A matrix might be different, or almost certainly is. And for both the Riccardi as well as the Lyapunov equation, there's an interesting observation that if the constant terms and the coefficients that are just mentioned are low rank, we can actually approximate our solution object by a lowering factorization. And many algorithms get simpler if we do so with a 3-term factorization. So that's what we will use later on in the package. These types of equations are typically referred to as large scale. Large scale because the general assumption is X is simply too large to fit in memory if stored as a dense matrix. So instead, we have to devise algorithms that operate on the Z and the Y factors directly. And the most commonly used algorithms there are all iterative ones, namely the low-rank ADI, as well as some Krylov subspace projection methods. And both of these have some form to describe the residual of these equations given the low-rank solution object itself as a low-rank term. So in this case, this R times T times R transpose. Most of these algorithms start with 0. So 0 can be conceptually represented as some 0 columns times a 0 times 0 matrix object times 0 rows of whatever dimensions we'd like to have at the end. And the iteration then concatenates some amount of columns to our order factor Z at every iteration. And that means our Z factor is actually what drives the memory consumption. Given we're large scale, if X is too expensive to store in memory, so are A and E. So these are typically large and sparse or even matrix free, so we can multiply with them, but we can't really factorize them in most settings when matrix free. But we'll try to optimize these now. And so let's have a look at some examples. Okay, first what the second aspect is. So first approximation was the lowering part. The second approximation that I will do, or I will talk about in this talk, is mixed precision. Meaning the most expensive part in terms of traffic, in terms of storage, is our Z factor. And so I would like to reduce its storage requirements by hopefully being able to use a lower precision data type. For example, going from IEEE double precision to single precision, cutting its storage needs in half. What that gives us is, if I need less storage to solve the equation, I can solve larger equations on the same hardware. Conversely, if the same equation has less traffic or has less memory to move through the CPU and back or through the compute device, there's hopes that the time to solution as well as energy to solution are reduced. So that's what we do. And why am I doing the ADI? When I started my PhD, I was told that Max Planck Institute in Magdeburg is kind of the ADI headquarters. And if you want to do Krylov methods, then you got to go to Bologna instead. So we start with ADI for this talk. And now let's have a look at some examples. One from a rather old example from the Oberwolf benchmark collection is the so-called chip example, or convective thermal flow. It's operators A and E are 20,000 times 20,000, so it's moderately sized. One could, in principle, also serve this densely, but it will take a long time. I have some timings later, because 20K times 20K gives you some 400 million entries in your solution object. It's 3 GB in size. While possible, we can compute a lowering solution that just takes 13 megabytes at more or less the same quality or same residual. And that's then what we should do. But we could also consider larger equations. For example, the steel profile in not even its largest configuration. It's an FEM discretization of cooling of a rail from some locomotives where the locomotives can drive on. And the operators here are some 317 or 300,000 by 300,000. So it would be absolutely insane to try to solve this in a dense fashion. So the X must never be assembled. Instead, we solve in the lowering fashion, and even there, our Z factor is only like 500 to 600 megabytes in size. So just as an introduction, in case I will use later on, I'd like to show you some code. One package goes alongside the DRE package, and that is the MoreWiki, because our research group maintains some benchmark data sets on MoreWiki, and I was lazy, or I got sick of downloading the zip files and then putting them in the directory, so I wrote a package that takes care of it for me and the caching in between different computing environments. There I have some simple structs like this Phoenix rail with one single integer argument that is the dimension of the Phoenix rail in this case. This is what I try to have this as speaking names, so people in the community would call this the Phoenix rail, and it's the 5,000 dimensional Phoenix rail in this case. Creating the Phoenix rail object is cheap, does not download any data, only if you try to assemble it. It's when you're asked to confirm the data download and it's stored. That gives me an EABC system, and then I can assemble some gradients of this EABC system that I then put together in a GALE problem struct that is the generalized algebraic Lyapunov equation problem. The interface there is inspired by what's happening in the differential equations community, in the SciML community. So I have this problem struct, and then I have an algorithm struct, in this case the ADI. But the big difference to the SciML interface is that most algorithmic parameters in my case are fields of the algorithm struct instead of keyword arguments to the solve function. That is because most algorithms that I have in the package have vastly different parameters, and it felt wrong to me to have parameters as keyword arguments that are never used, and always had to carry on some collection of all the remaining quarks of their function, and then only some of which are read, and the user does not know which ones, and you might get some odd behaviors there. So then you solve. X is again a lazy lowering object that's coming back, and then I wrote some methods for norm and addition, subtraction, so you can do more or less easy math with these objects. And in this case, we can compute the residual. So in terms of the previous slide, there was the L operator of my solution object, and is in code written as residual of problem, and my solution object gives me another lowering object. I take the norm that does some fancy lowering arithmetic, and then I get some object that has here a relative tolerance of below 10 to the negative 10, as I had requested to do so. And because the package is called DRE-JL, I'd also like to show you some DRE example. Same Phoenix rail. I assemble the initial value as I showed you on the previous slide. Configure the time span. For this particular problem, the canonical time interval is the 4,500 to 0 backwards in time. And then have a Rosenbrock scheme, a first order Rosenbrock. And then I give it an inner solver that is the ADI I can configure, and I can give it maximum iterations, relative tolerance. I can give the shift parameters that I need. I will show you later how that looks like. And only here I have like the DT as a keyword argument, but that's for historic reasons. And so then the solution object come back has the time, the feedback, and the X. So if that's all you're going to take away from this code, my talk is, I hope I could convince you the interface is somewhat easy to use, and all the differentiations, whether I have a standard equation or a generalized equation, boils down to passing an identity object in this first position to my problem, or a legit matrix object E. And other than that, it's all solved. And I hope when you're staying with me, I can convince you that there is some merit to it. Currently, I have not only the ADI, with some rather fancy options to it, the index ADI. I have a GMRS method that I can precondition with my ADI, And if I don't want a precondition, I just plug in nothing. So the default value for most non-trivial arguments here is always nothing. And what this allows me to do is, for example, I can have a GMRES for Lyapunov equations that is preconditioned with a GMRES that is preconditioned with an ADI. The code to express this is really easy. The runtime performance is not there yet. So my main workhorse here is the ADI, but it's possible. And for prototyping, I have also a Barter Stewart and a Kronecker, which convert my coefficients to dense form and then call into matrix equations or just assemble the Kronecker form, just for benchmark, for testing, prototyping, and stuff. All right. That was the introduction. Next, I'd like to talk to you about Lorenz arithmetic and how I can rephrase standard algorithms for the large scale or the low-rank setting. Then give you some more background on the IDI method, to then show you how I'd like to get mixed precision into the picture before I conclude the talk with a small summary and outlook. Lorenz arithmetic. So how can we get the memory, keep the memory consumption in check? So how do we avoid forming the product of the zy and the transpose? There's actually many operations we can do with a three-term factorization. We can add two such objects by just concatenating the outer factors horizontally or vertically, depending on the left or the right. And the inner factors are just being concatenated diagonally. And here you see that the scalar coefficients, alpha and beta, just go through the center term. And what that gives you is I can not only add these low-rank objects, I can also subtract them without leaving my representation space. There's an ongoing debate on whether algorithms should compute a three-term factorization or a two-term factorization at Cholesky type. And I'm a big proponent of the three-term one just because it keeps the mathematics simpler and the algorithmic description. When I need to compute the norm of such a low-rank object, I can, instead of computing the big, assembling the product, compute the QR decomposition of the outer low-rank factor, and then make use of a unitarily invariant norm. So this works for the two norm as well as the Frobenius norm. I can just discard the Q factors, and what I'm left with is a much, much smaller object. If you remember the examples where the outer factors was like 300,000, the solution object was only like a few hundreds or so. And this small norm is actually very feasible to compute. Lastly, when I have iterative algorithms where I keep on adding components onto components onto components, I will inevitably collect some redundancies that I need to get rid of. And when compressing those features back down, I use a very, very similar approach. I take that same QR decomposition, but then compute an eigen decomposition of the inner object, where it's then trivial to discard certain components based on the eigenvalues of the inner diagonal factor. So for the package currently, I think there is a dimension times epsilon based cutoff on the ratio of the largest and the smallest eigenvalue I will keep. But I have plans on making that configurable as well, so in case you want to try something else or just need something else for your applications. And then I undo this decompositions and get a new low-rank object with an typically orthogonal factor as the outer low-rank factor. Next operation I'd like to show you is a low-rank dot product. And that can be rephrased as the sum, an embarrassingly parallel sum of some generalized dot products of small objects. And remember, these are the columns of the white factors. So these are potentially 300,000 many that I have to compute the sum of some 300,000 generalized dot products. And that can also be done rather efficiently and can utilize hardware. Potentially. Currently, while I have it implemented, I do not have it parallelized yet. That's why the GMRES is still experimental. So what's the workhorse of the package? It's exactly the lists that I just showed you of the sum of objects. I have a list of scalars, I have a list of outer low-rank factors, and I have a list of inner low-rank factors. What that gives me is addition is merely a concatenation of these vectors, of these lists of factors. To be independent of how you name your variables in the code, there is a constructor named just low rank. So if I say x equals low rank of L and D, that gives me a lazy product of L times D times L transpose. If I want to get a scalar into the picture, I just multiply the result of it. If I multiply this whole object by a scalar, I am very slow, I noticed. I just multiply the list of scalars, so it's also a very cheap operation. And only when I want to compress this object or compute a norm, then I actually concatenate the objects, and that's when it becomes expensive. All right, ADI. ADI in a nutshell. Given some lowering factorization as input, I have an incremental form where I'd always keep on adding some lowering objects. So not only my outer factor grows with each iteration, but the inner factor just gets this Kronecker structure in the end. And so the Y is cheap because it's small, but it's even cheaper because there's algorithmically not much going on. In a slightly larger detail, I can initialize the factors of my solution are Z and Y. Then I have the residual outer factor, which is named R, and the inner factor is T. And they are initialized with the right-hand side object. That's another nice aspect. If I start with 0, everything becomes nice, looks nice because it's just the constant term of my Lyapunov equation. And then I have this back and forth. The residual determines the increment, and the increment V then determines the residual again. And during that iteration, I just have to collect all the increments to assemble my solution. Or if I'm interested in a feedback or other derived quantities, I can just update those based on V. So there's a rather cheap computations to it. And the most expensive part in the ADI itself is the solution of these shifted linear systems, A plus E transposed. And I need good shift parameters. That's also not trivial to come up with. So how do I configure that? I can do different linear solvers for those problems. I can do different shift parameters. And for that, I have written some adapters. One is called with quarks, that I can give any solver object from the linear solve package, and a collection of keyword arguments that, when applied to a block linear problem or a linear problem, are translated to the keyword arguments that linear solve requires, but I require them in the solver struct. And then I have the column-wise adapter that initializes the solver cache once and then loops through all the columns. For the shifts, similar picture. I have also these oracle structs that just define the algorithmic parameters, but are not expensive otherwise. And that also needs sometimes to solve linear systems, so I can use the same block linear solver there and plug everything together with the ADI, and it can solve a Lyapunov equation. Or I can even plug it into a Newton's method, and then I have a Newton ADI to solve an algebraic Riccati equation. All right, so I strive to have simple things easy, yet complicated or complex things possible. And if there's a certain aspect you would like to try, different linear solver, block linear solver, different shift strategies, different norms, not yet, different also normalization strategies, not yet, that should be possible without requiring any changes to my package. That's why I'm heading towards. All right, and remember the picture from the beginning. We'd like to reduce the storage needs of the outer factors. So in this picture, it's the orange part that I like to use a cheap data type for, while for the others, I'm completely fine with having some more expensive data parts, storage parts. And the question is, does it work? And the answer is not really. Here we see on the horizontal axis the ADI iterations. On the vertical axis, we see in the bottom row the explicitly measured residual of our equation. So the Lyapunov of our x, lowering norm divided by the norm of the initial object. And in the top row, we see the implicitly updated residual that is maintained throughout the ADI iteration. And the columns are then 3 different benchmark examples. So let's stick to the first row for a moment. Excluding one exception, it always looks like convergence. I was requesting a solution to a relative tolerance 10 to the negative 10, and the implicitly updated residuals all look like convergence. But when we actually explicitly measure what's going on, we see that the purple curves that are here, some components stored or computed in single precision detach from the implicit ones. And only for the orange ones, where there's actually all double precision computations, we stick to the implicit measures. But if our problem is somewhat difficult, even the double precision stuff detaches. So all implementations I know only measure the implicit residual objects. There is merit in every once in a while also measuring the explicit ones to see whether we've detached, and then there's little hope that we will get back to that. In terms of runtimes, there's some stark differences. So these are same measures we just saw on the plot. And I'd like to draw attention to the runtime part, where there's usually a factor of 4 if we solve the linear systems in a single precision. And the dense solvers, the Bartlett-Stewart method, are just orders of magnitude larger. So for the chip example, which is 20K by 20K, we're talking like 9 seconds versus 19 hours. And that was a rather beefy machine. I think it was some AMD EPIC with 64 cores and however much memory you can imagine. What did go wrong? Was it the single precision stuff or was it something else? And my approach was rather naive to single precision. I want to reduce the cost of the most expensive object, and that's not as easy. There is a paper by Patrick Kirschner and Melina Freitag that devise an inexact ADI and inexact trade-off methods. And one of their key results is I have to solve very, very accurately for early iterations of my ADI and can be a bit sloppy on the later iterations. So when changing to single precision, I was very, very inexactly computing solutions at the early iterations. But I could do the same when I just replace my solver. I want to compare different precisions, and so I tried to keep all other things equal. And because native Julia doesn't have a single precision LU, the sweet sparse package behind it computes a double precision copy, factorizes that, and truncates it back down to single. That's not the behavior I intend. There's like, yeah, while it's accurate, it leaves all the performance that I hope to gain on the table, and I thought that was not a fair comparison. Therefore, I switched to GMRes. And later on, what we see here, the same ADI trajectories versus the explicitly measured residuals, but I only compute a certain number of iterations from the beginning with the LU, and then I switch to my less precise GMRes iteration. And here we see if I only do one step, if I do GMRes throughout, I plateau rather high. And it's the same plateau that is that I get to when I have 1 or 2 steps of LU before I switch to GMRes. But here, if I have 15 steps of LU, so for this single example, until the half the number of iterations needed to reach target accuracy, and switch afterwards to GMRes, I still reach target accuracy. So the naive approach was just not a good idea. Instead, I should have started with double precision computations, and once my heuristics, that paper gives me access to, the Kirschner-Freitag paper, permitted it, I can switch to single precision later on. That would be a much more sound approach, which I now have more numerical evidence to. So, mixed precision. Why I was hitting a wall. I was trying a rather unobtrusive approach. That is, my solve routines have 2 more keyword arguments that have to be keyword arguments because they depend on the problem instance being passed into. In this case, the initial guess as well as the initial residual. And whatever data type they have determine the types used during the computations. If there's nothing passed into it, the data type of my constant term in the Lyapunov equation determines the type of the solution and everything else. But in this case, the type of the initial guess is retained to the type of the solution, and the type of the initial residual is retained to the type of the increments. Back in the day, it felt nice. I had really simple code in order to get it running on the GPU, which I used with the same approaches. It was like only 100 lines of code or so that needed changing. Was somewhat nice, but it's also limited in the sense that if I have some nested algorithms like Newton ADI or so, where I want to have the inner algorithm, the ADI, in a lower precision than the outer one, I would now need some adapters that do the type conversions and stuff. And so what felt like oblivious here would be explicit later. And so I still have to figure out what's a way to it that's also fun to use. One such way I tried was, because I did not want to give up on the idea, was a notion of a mixed precision number, mixed precision float, where just in the Julia type system, I only store it in a cheap storage precision, but basically have all computations that are going on promote to the working precision. If I then want to store back in the storage precision, I would expect the user to have allocated some storage with similar. So the similar would then be of my mixed type again. The computations are in the working precision, but when I write the working precision objects to a mix or a vector of mixed, they would be truncated again. So that sounded like a promising approach, but as soon as you need all the other details, when you try to use these numbers in other packages, things start to fall apart. For example, the Krylov.jl package, I wanted to use the GMRES solver from Krylov.jl, requires the epsilon of a mixed object to be of mixed type again. And so this, I couldn't find the codes anymore. While I eventually got it running with Krylov.jl, the residuals they obtained were not as nice. So, summary and conclusion. I have a package that allows you to solve algebraic Lyapunov equations, algebraic Riccardi equations, and differential Riccardi equations with a small collection of solvers, but there could always be more. I tried to provide an interface of algorithm structs that is composable. So here's actually one missing. If one were to implement a rational Krylov subspace method, an RKSM, I would actually need a dense solver inside because it's projecting down, and there I would have some choice again. I could also use some direct Riccardi solvers like Radi that I could use in some other integration schemes like backwards differentiation formulas. And if I really want to use mixed precision, I should employ some stabilization schemes. So for GMRES, it's typically iterative refinement, and that can be really neatly expressed with ADI with very little overhead. And in a recent collaboration with Pascal Den Boef from the Netherlands, we generalized the reduced rank extrapolation to such matrix objects, and that could also make work as a stabilization scheme. So lots of things to try out. And in general, improve the support for the standard equations if I just pass in the lazy uniform scaling objects. ADI works quite well with that already. The differential equations, I did not test whether they do a reasonable thing. My test harness, my CI is green, but I might have missed something. I mean, I wrote CI in the end. I can always improve the robustness of the ADI. I'm considering to extract the lowering arithmetic as parts of the package because most of it is actually independent of it, and it might be useful to others. But in the end, I would be interested in what you would like to use from the package. Does this provide some functionality that you could use? If so, I'd be happy if you could try it out and let me know where it breaks for you. Or if it doesn't, then I'm even more happy. Here's some further reading, and then thanks for your attention. No. Okay. Then next speaker. Sorry for going over time a little bit. I would like to introduce our next speaker to you, who is Vicky Karika, who is an undergrad student at MIT. And in collaboration with Rabab, Evelyn, and Alan Edelman, they all wrote a symmetric rank K update or some symmetric solvers, hierarchical precision, and recursion for accelerating linear algebra on modern architectures to have some performance portable linear algebra. I'm very interested to hear the talk. The stage is all yours.
Well, okay. Hi, my name is Vicky Karika, an undergraduate at MIT with the Julia Lab. Thanks for having me. So modern computing architecture is changing a lot recently with the introduction of AI, making low precision super fast. But this leaves behind the scientific computing community that still needs accuracy for their solutions. So the challenge is, how can we use this new architecture to get performance while not sacrificing as much accuracy as if we use this low precision everywhere. And to try to address this, we've been working on a mixed precision nested recursive framework for accelerating linear algebra on these modern GPUs. So I'll be going over the motivation, like why mixed precision is needed for linear algebra, and specifically why I'll be focusing on Cholesky for this talk, the solution that we implemented, and the results that we were able to get with the framework. So let's begin by talking about the architecture. Modern AI hardware has these things called matrix processing units, or MXUs, which, for example, are NVIDIA Tensor cores or AMD matrix cores on their modern GPUs that heavily prioritize low precision throughput, such as FP16. So on the left here, we can see that FP16 is 58 times more computationally advantageous compared to FP64 for these GPUs, such as the NVIDIA H200 GPU. And our goal is to leverage this huge compute advantage without sacrificing the accuracy from FP16. So this introduces the idea of mixed precision. The general strategy of mixed precision is taking a problem and applying low precision that's fast to the majority of the computation, while we apply high precision to the most accuracy critical parts. Here in these pictures, we have a picture of my mom who works on computational fluid dynamics, and she could use mixed precision because she still needs accuracy, but also is always looking for more performance for her simulations. So there's an example of why it's necessary. I'm specifically going to be focusing on Cholesky for this talk because Cholesky has a nice recursive decomposition to it that we leverage, and it's also very used in a lot of scientific computing, such as CFD, my mom uses it, robotics, finance, and more. And more formally, it's the decomposition of a symmetric positive definite matrix into a lower triangular matrix and its transpose. We choose Julia to write our implementation in because it allows us to have a single, concise, readable code base for all vendors, having a portable implementation. Right now, we're using multiple dispatch to route to vendor optimized base cases once we get to the leaf of our recursion, but we also have been working towards writing kernel abstractions kernels for our base cases, which would allow us to have one single custom kernel that would run on NVIDIA, AMD, Apple, and Intel. Okay, so a recursive Cholesky algorithm is a very well-known algorithm that breaks down Cholesky into POTRF base cases on the diagonals, and then a triangular solve and a symmetric rank K update on the off diagonals. But we take this one step further, also breaking down the triangular solve and the symmetric rank K recursively as well, leading to this like nested recursion. And what this does is that it allows us to expose these gems or matrix multiplications on these off-diagonal blocks, which allows us to have more parallelism, but also critically we do these off-diagonal blocks in low precision, which is where we get this compute advantage from these fast matrix multiplications. So in order to introduce mixed precision into our algorithm, we made a data structure that has different blocks and different precisions in different parts of the matrix. So here's an example of what one might look like, but we allow the user to put in the amount of recursive layers that they want, as well as what precision they want on each layer. In this example, we have FP64 on the diagonal, FP32 on the next two layers, and then FP16 on the next two layers. Because of the nature of the matrices that we work on and the symmetric positive matrices, we typically have matrices that are more, that have larger values on the diagonal. So we say these are accuracy critical parts and cast low precision onto the off diagonal and higher precision onto the accuracy critical diagonal for our cases. One of the challenges that mixed precision and low precision in general has is that FP16 has a very limited range compared to FP64. So if we begin with a matrix that's FP64 and then make our data structure, we might get overflow or underflow. So what we did to address this is that we used a very lightweight per block quantization step that, like, if, for example, our off-diagonal block there has 100K, we would scale it down to make sure that it fits within the range of FP16, run our algorithm on that quantized data structure, and then dequantize it back after the algorithm is finished. Okay. Results. So TRSM and Circ take up 61% of the time of Cholesky. So in order to have a fast Cholesky, we also need a fast TRSM and Circ. We do both of them also in mixed precision. So here you can see the results of that. For TRSM, for runtime ratio compared to cuBLAS, which is state-of-the-art on the NVIDIA H200 GPU, we get a 5 times speed up for the best mixed precision scenario with FP16 and FP32 compared to cuBLAS and pure FP32. And for Circ, we get an even larger speed up, getting about 12 times for mixed precision, and pure FP16 gets a giant 70 times speed up, showing how these tensor cores really can speed these routines up a lot. And then for Cholesky, we also got similar speedups. Here's kind of like a big picture. For accuracy, as expected, a mixed precision scenario with 2 different precisions is basically right in between the 2 precisions. For example, one with FP32 and FP64 sits at about 10 to the negative 12 between the pure FP64 and pure FP32. And you get similar trends for runtime, but I want to highlight these ones here using FP16. For the mixed precision scenario, using FP16 on all the off diagonals and FP32 on the diagonal, we get over 5 times speed up compared to the cuSolver FP32, while having 10 to the negative 6 accuracy, 100 times more accurate than if we did pure FP16, while getting almost as much runtime as a pure FP16 implementation. As I noted, we do have portability with multiple dispatch currently. We have similar scaling trends when running on AMD GPUs and NVIDIA GPUs, but the overall speedup is more modest for AMD GPUs, getting only about 2.2 times on a 32K matrix. And this is because mixed precision matrix multiplication support for AMD and Julia is still a work in progress in our lab, but we hope to have that soon, and we expect that the NVIDIA and AMD performance speedups should be approximately the same once we have that. And then I wanted to note that because of the nested recursion overhead, this is better suited for larger problems. Namely, below about 8K by 8K, our implementation is slower, and then we see these really big speedups once we get to about 32K or 64K matrix size. And also recently, one of our projects has been that we've been working with LLM fine-tuning and in-context learning to see if they can kind of learn this framework and expand it beyond Cholesky to other algorithms. Here's quick results for LU, and we were able to see about a 5 times speed up for LU as well, getting similar results as Cholesky, showing that it's not just a one-hit wonder, and it works for other solvers as well. However, it is important to look at the limitations in real-world evaluations. We find that our solver is most effective for dense matrices, that's what we're working with currently, that are relatively large, 16K and larger, and diagonally dominant. We tried it on Body 5, which is a NASA structural data matrix that's sparse, and 18K by 18K, which is somewhat on the smaller side. And we did get the expected accuracy, but the runtimes speedups were more modest than in our matrices that we generated. Another thing to note is that extreme dynamic ranges, even though we do have that per block quantization scheme, can break positive definiteness. So there's still more efforts being made to find a better quantization scheme that will be better suited for a larger array of matrices. We're also, I mentioned before, working towards full portability with kernel abstractions, and some kernels have been implemented so far in an effort to do this. We have a TRSM and a POTRF, which is a Cholesky kernel, and for 256 by 256, we get 86% and 44% speed up compared to cuBLAS and cuSolver respectively. We do want to get nearer to the cuBLAS and cuSolver speed, so it's something that we're working towards. And our current trade-off would be exchanging that peak vendor base case for true hardware autonomy. So that is something that's currently in the work as well. But the runtime results were all for the vendor base cases. And then I want to just say that the overall goal of my group and my lab is to have accessible, performant linear algebra. So we know that there's many future steps for us still to do with this project. Namely, one of them is that we want to work with sparse matrices, because we are aware that a lot of the scientific applications that would use this are for sparse matrices. So that is something that we are currently working towards. We also want to extend to further routines like QR, and we are working towards full portability, as I mentioned. So, yes, that is the presentation. Thank you for coming.
Thank you for the talk. Do we have questions?
Hey, great talk. I have one question about the data structure you showed with the, I think it's also on the current slide, or you can also go back. Is this, is it dependent on the matrix or on the method you're using, that you're using like this specific data structure, or could you like, is this like an optimal for like all kinds of methods, not only Cholesky or LU, you're using it, and is it also dependent on like what you're solving, that you have like a matrix which is dominant on the diagonal if you compare to have your different matrix which you don't have that anymore?
Yeah, we've tried a few different types of matrices, but the motivation for having this kind of recursive matrix is that it works very well with the recursive algorithm and hand in hand. And also for a lot of the matrices that we are testing, we noticed that we would want high precision on the diagonal kind of blocks anyway, so this kind of data structure is well suited for that. But we have looked into kind of tiled data structures for mixed precision, as well as kind of like a tiled and recursive data structure where like the blocks themselves would be like tiled. So yes, data structure, there's a lot of work also going into that, and that's a good question. I think for Cholesky, it kind of worked out that this kind of like the more simple data structure worked well for the problem. Yeah.
Hi, nice talk. I guess one question that I had was these lower precision operations that you're using on the off diagonal. Don't you still have the issue that the TRSM, the triangular solve, is somewhat latency bound, since you do a triangular solve on the diagonal, and the update itself, though it's like quite computationally, like you can get a lot of computation packed in, you're kind of hitting like maybe the lower, like less heavy portion, and you can't really solve the latency boundedness. I don't know, like what your...
Yeah, I think the reason that we get speed ups for like the recursive TRSM, for example, with mixed precision, is that we do recurse on the TRSM and it exposes the gems there on the off diagonal, and that's what's really giving the speed ups, not the TRSM itself, if that makes sense, like the base cases.
Yeah, I mean, I guess maybe to like hone the question a little bit, these are like relative comparisons to the cuSolve, right?
Yeah, to cuBLAS, yeah.
Or to cuBLAS.
Yeah.
So you still have like this latency bound. I was just curious, like, did you benchmark the kernels? Like, which percentage is latency bound? Maybe it
No,
increases?
I didn't. That's a good question, though. Yeah.
Thank you.
Okay, thank you for the talk. Can you turn to the page of the recursive data structure?
Yes.
Sure. So I'm wondering, what is the corresponding memory layout for this kind of structure? Because you know, the memory layout can affect the speed a lot, and
Yeah.
I'm not sure if this is good for the data communication architecture for the accelerators.
Yeah, so for the data structure, we store, well, we have like an original matrix, say it's an FP64, and then we take views of the kind of like the these blocks, and then store anything that's in a different precision, as a separate new block in memory. Because it's symmetric, we can exploit that and only store one of the off-diagonal blocks. But yes, we do take up more memory by having to do these data structure, making a new data structure at that step, if that makes sense.
So in the end, the off-diagonal elements are stored separately in the memory, not close to the
yeah, they're stored
diagonal
as separate like matrices. Yeah.
Okay, I see. Thank you.
Yeah, but for the runtimes, the step of converting this into the data structure is included as a part of the runtime for the algorithm. So we take that into account.
Do you want to take more questions? So we don't have.
How are we doing on
rush.
time? I can do another
There
one.
is just a discussion afterwards, so
Okay.
we can delay that.
Hi, thank you for the talk. This is kind of related to a question I was asked earlier about this structure and sort of like prioritizing the entries that are like close to the diagonal. I guess just from some things that I've seen in like kernel machine learning, sometimes like you might have something that's very far off the diagonal if like maybe your points are just organized in a weird way, because it kind of just depends on how you label your points a little bit, what's close together. So is there ever something you have to look at, maybe like permuting the rows and the columns to maybe organize the points so that the actual important ones are close to the diagonal?
Yeah, that's a good question and also a good idea. I think for the matrices that we looked at, they were pretty well suited for this kind of data structure. And maybe if you have a large value that's kind of in the off diagonal, maybe a tile data structure might be better in that case. Or the permuting the rows and columns is a good idea. I hadn't thought of that. It's not something we've explored, but yeah.
Well, thank you.
Thank you.
All right, do we have more questions? If not, then let's thank Vicky again.
should we start? Yes? So, hello everyone, I'm Léo Batti, I'm a research engineer at Cermix lab at École des Ponts. And for this talk, we'll talk a bit about decision-focused learning, and in particular about Julia decision-focused learning and the ecosystem of Julia packages in order to do decision-focused learning. So the goal of this talk is that by the end, you all know what is decision-focused learning, and if you encounter one day a problem that can be solved with DFL, you know where to search for and what packages to use. So I won't enter into the details of the maths. I will stay high level and focus on the practice and on the code to use. So let me start by introducing a small toy problem I will use as a starting point to showcase all the different features we have. So it is a very simple problem that can be solved using decision-focused learning. So it's the stochastic contextual assortment problem. So imagine you have a store, you run a store and you have n different products. Each product has a price, takes some size, some shelf size, and you have a limited size of your shelf. And your goal is to, before your next customer arrives, is to choose what you display on your shelf. And so you have a limited space. And so for each item, you need to choose if you display it or not. But you don't know exactly the customer preferences. You only can observe some contextual information about their preference, but it's more some information that is correlated and not directly the preference. So here you have stochastic optimization problem where you make a decision before you observe some uncertainty, and the decision space is combinatorial. By combinatorial, I mean it is finite, but if you increase a lot the number of items, you cannot enumerate all possible solutions. So this is the setting I'm in, and the goal is to find a policy that makes decisions so that we maximize the expected revenue. And for that, we will define what I call a decision-focused learning policy, which is this thing here. So as input, we observe the instance parameters, so all the items we have access to, the shelf size, some contextual information about the customer. And as the output, we want an assortment that fits in our shelf and such that we maximize the revenue that the customer will buy. And for this, we introduce two components to build our policy. The first one is a neural network or any differentiable statistical model that takes as input my instance, my context X, and outputs for each item some score, theta. And then we feed those scores inside a combinatorial optimization algorithm. Here it's a simple knapsack problem that tries to fit as much total score as possible, but while respecting the shelf size constraints. So this is a policy that, given any input, will give you a feasible solution. And the goal is to find the parameters W of your neural network such that the policy gives good solutions in practice. So this is the policy for the specific assortment problem, but you can imagine the same policy for a lot of different problems. So in the general case, we have an instance X, we want a decision Y, which is pi of X, and we want that our policy outputs a good solution for the metric that depends on your problem you considered. And then, so we have this first components, which is the statistical model that outputs a prediction theta. And we use this prediction theta as input of a combinatorial optimization algorithm that gives you a feasible solution. So these are the first two components we need to build decision-focused learning policies. And we still have a need for two more components in order to be able to find the parameters W such that we have a good policy. The first one is a data set, since we want to use machine learning to train our full policy. And we need also a learning algorithm in order to find the right W that uses the data set. So I won't go into details of the math, as I said. So what we do in practice is we choose a setting, supervised learning if we have target solutions, good target solutions to imitate, or direct empirical risk minimization if we do not have. And we try to define some loss function. The issue is that in practice, the combinatorial optimization algorithm is it's difficult to backpropagate gradient through it because it's piecewise constant most of the time, so that you need to add additional techniques in order to smooth your Oracle F or define some differentiable losses to be able to find informative gradients and learn your model. And this is decision-focused learning. If you want more details about the math, there is a recent survey on the field. I put the link here. And now let's talk about the Julia ecosystem. In Julia decision-focused learning, we have three main packages. The first one being inferop.jl, which is the first packages we created in the, about decision-focused learning. It provides the core building blocks to build your differentiable optimization layer and losses. So it's a very low-level kind of package that builds automatic differentiation rules, etc. And then we have two more recent packages that builds over this package. The first one is DFL benchmarks, which provides a bank of benchmark problems that can be solved using decision-focused learning. And it provides a generic interface, a generic API to define your own benchmark problem, so that once you plug it in the generic interface, then you have access to all the ecosystem features. And finally, the most recent package is DFL algorithm that provides a set of ready-to-use state-of-the-art algorithms to train decision-focused learning policies. I will show you a demo of these two packages at the end. What's interesting is currently these three packages are compatible with the optimization ecosystem in Julia, like Jump, and the machine learning ecosystem with Flux and Zygote. So it's compatible. Okay, so let's talk a bit about what's in DFL benchmarks, a bit more in details. So we have a list of different benchmark problems that we split in three different categories. The first one is static problems, the simpler ones. That are, there is the abstract benchmark type you can subtype to define such benchmarks. You have the abstract stochastic benchmark interface. The assortment problem I just introduced at the start fits in this category. And there are, if your optimization problem is dynamic, if it's a multi-stage stochastic optimization problem, you can also fit in the more complex category, which is the abstract dynamic benchmark. So what's the end goal of all these new packages? There are two main goals. The first goal is if you want to solve a new problem, you implement it using the common interface. And then you can use all the algorithms in DFL algorithms and directly apply in a few lines of code, apply them and test all of them on your problem. And on the other way around, if you have an idea for a new algorithm to train a policy, you can define it inside the DFL algorithm interface, and then you can apply it to all the benchmark problems that are already in DFL benchmarks, and you can compare it with the already state-of-the-art algorithms that are already implemented in DFL algorithms. So these are the two goals: is to provide packages that makes research about decision-focused learning a lot simpler and faster to iterate. Okay, so here is an example of how you would of the interface you need to implement in order to plug in your problem to DFL benchmarks. So you need to define a data struct. Here, this is the contextual assortment benchmark. That is a subtype of the stochastic benchmark abstract type. And then you need to define a bunch of methods. Some methods to be able to generate instances and data. So you have a method to generate the fixed problem data, a method to generate your observation, the context about the customer in the case of the assortment problem, a scenario generator, and the objective value, which is the metric that decides if a solution is good or not. And finally, you need the two main methods are generate statistical model in order to initialize a statistical model for your policy, and generate maximizer that generates your combinatorial optimization solver in order to build your two components of the policy. And finally, there are a lot of optional methods you can implement. For instance, the generate anticipative solver that is useful if you have if you need to apply a supervised learning algorithm. You can use it to compute target solutions for imitation. That's what we will use in the demo. And you have some also methods to plot, etc. So these are the main methods. And yeah, when you generate any data, the output of this generate data methods are data samples, which is a custom type we have inside DFL benchmark, which contains a few fields. So the input X you feed to your statistical model, an optional target solution if you need it, some context information, and some extra fields as you need. And when you have these data samples type, it's quite easy then to apply your policy. You just apply your model to the X field, you get your theta, and then you apply your maximizer to the weight theta, you give it some context fields if you need, and you obtain your decision. And once you define all this interface, now you can easily, in a few lines, define your policy. So you can generate your first components with generate statistical model, generate your second component using generate maximizer, create a dataset through the method generate dataset that calls all the sub-methods you defined. And then we need a final component, which is the learning algorithm. And that's where we pass to a decision-focused learning algorithm package in order to define our policy and choose one of the algorithms in the package and apply the train policy method that gives you that gives you your train policy as output. To be more concrete, I will show you a small demo on the assortment problem. So here I have a Pluto notebook. So I will share the link to the notebook so you can toy around with it you have a lot more details on the problem in it. But I won't go over the details, but I will show you a bit how the code is in practice. So here I define the details of my assortment problem, the number of items and some internal parameters. Then I define the generate instance method, which outputs a data sample that contains a custom struct that defines the data of my problem. Then the generate contexts methods takes as input this instance sample and builds the context information by sampling a new customer. And finally, the generate scenario takes as input this context information and returns some scenario that is here also a custom data type. That's not a problem. And we define the objective value, which is the revenue. And finally, we define a statistical model which returns a flux, a small neural network for the example with 2 layers, and the generate maximizer, which gives the knapsack, which is a knapsack method. Here we solve it using dynamic programming, but you could solve it with a mixed integer program. It's not a problem. It can be any Julia callable. It will work out of the box with any of the algorithms. And finally, to compute the target solutions, we define our anticipative policy that assumes that we know the future, so it chooses the best solution, and we use this as the target solution. Okay, and then you can define also some plot utilities with the plot sample method, and that's it. We have defined our benchmark, and now we construct our benchmark object. We get our anticipative solution, and we can define some data sets, so some test data, some trained data that is labeled with our target policy. We initialize our statistical model. We create our combinatorial optimization solver. We can also define some metrics, and we can visualize our data set using the plot function we defined above. And now, so I gave here some maths about the supervised learning algorithm we choose. So we choose this one. We define our policy and apply the train policy method and get as output our policy. And here we see what happened during the training. Here you have the average revenue depending on your epoch on the test data, and we see that it's not good. The algorithm did not work. That's because the assortment problem is quite particular, and if you use anticipative solutions as target solution, it won't work at all because they are quite degenerate. So here we see that, okay, this algorithm did not work in this setting. So can we swap the algorithm? How do we do that? We just need to change one line in the code, which is the algorithm you use to train your policy. So that's what we do here. We replace in the train policy our previous algorithm with a new one, which is the mirror descent one, which is a bit more complex. It's an iterative alternating minimization algorithm. If you want more details, I put a reference here. So it's a bit more complicated. It takes a bit more time to run comparing to before. And then we can look at some results, and we see that the revenue increased. This new algorithm seems to work better on this case. In this case, so we have an average revenue on the test data that is higher, and it seems to have learned something. And we can visualize, if you want, the solution we output on the test data. And that's nice. So we have found an algorithm that works. But now, imagine you have a new benchmark problem and you want to test the same algorithm on the new benchmark problem. What you do? You define your benchmark problem, and then you change one line, the benchmark assignment variable, which is somewhere here. So for instance, I can use one of the benchmark that is already in the DFL benchmark package. This one, I think. Let's see if it works. Okay, so here I have a new visualization because it's a new benchmark, so I don't have time to explain. It's a another simple toy problem that runs quite fast so that I can showcase it. So here we see that the first algorithm works directly. We don't need the more advanced one on this case. We have the revenue that increases. And so that's nice, and everything run. And yeah, so that was for the demo to see how it works. Okay, so as a summary, if you want to change the algorithm, you change one line. If you want to change the benchmark problem, you change one line. And then some final words before questions. So what is the current state of the ecosystem and what are the next steps? So currently, because we started back in 2022 with the infrared package, we are under Flux and Zygote for the machine learning part and AutoDiff. We are currently interested in looking at supporting Lux plus Enzyme AutoDiff. So that's one of the next steps. The algorithm package is quite young for now, so we want to add more algorithms that are missing currently, such as the structure reinforcement learning methods. The most important line of the talk, if you try the packages and have any feedback, all feedbacks are welcome. That helps us a lot, improving the package, having any feedback on if they are positive or negative on all the packages. And finally, some links. So here is the link to the organization with all the packages and the link of the slides and the demo notebook. You can find it at this link. Thank you. Any questions? Okay. Okay, the question is, do I specialize on this kind of problem or another type of problems?
No, like in optimizing this kind of problems in general, or are you working on a specific real life?
So I did my PhD in collaboration with Air France. So I looked at a lot about transportation problems. So like aircraft scheduling and something like that, stochastic aircraft routing that are subject to delays. So you have a lot of transportation problems you can solve if you have uncertainty. You can solve them using this kind of method. So I looked a lot about these methods in particular. Yeah. Yes?
Elaborate a bit more about the link to reinforcement learning?
Yes. So I think last year we released a paper about so when you do not have target solutions, or if target solutions are bad quality, you want to be able to minimize or maximize your cost function directly. And one way to do it is using reinforcement learning. And I call it structured reinforcement learning because we are in a case where we are in a multi-stage stochastic optimization setting where at each time step your action space is combinatorially huge. And in this case, you cannot apply directly the reinforcement learning methods, and you need to mix reinforcement learning and decision-focused learning. That's what I meant by structured RL. We have a paper on this. If you want, I can give you the link. If there are no more questions, can go to the next talk.
All right, I think you can hear me now. Yeah, thanks everyone for coming. It's good to be here. It's my second Heimspiel, as we would say in Germany. I took the train here, and I got to do the same 2 years ago when I still lived in the Netherlands, to go to Eindhoven. So yeah, it's good to be here. This is the last piece of my PhD, which I finished earlier this year in February. This is a paper on counterfactual training, as the title says, which uses one technique from explainable AI, in particular counterfactual explanations, to teach models during training to basically make predictions based on what we define as plausible and actionable explanations. What's Taija? So Taija is essentially an organization on GitHub that just hosts a couple of different packages that research packages that I built and developed during my PhD. The main one is counterfactual explanations. I'll go on to explain a little bit about what that is. There's also some work on predictive uncertainty quantification, and most recently hybrid learning. So counterfactual training falls into that category. So most of you will probably be familiar with kind of standard model training. In this context here, supervised learning, we have a loss function, so we just had that in the previous talk as well, over some model predictions and some true observed outputs. And the goal in training is to minimize that loss by tweaking the model parameters. So that's our free kind of tweaks in the model itself that we can change. And in deep learning, we do that by, oops, that's a bad slide. Well, the maths is there. So in deep learning, we do that by backpropagating through the model and essentially taking gradients with respect to the parameters, and then we end up at an optimal solution theta star. Now, in the context of counterfactual explanations, we essentially invert that problem. So we now have a trained model. We have our parameter theta star here that parameterizes the model. But the problem that we have in explainable AI, or in AI more generally, is that models are typically, if you think of neural networks, they're black boxes. So we cannot easily look at model parameters and say, this is why the model makes a certain prediction. So what we do in counterfactual explanations is essentially taking the model as given, and now we do gradient descent again. We optimize, but this time with respect to model inputs. So we're asking ourselves, if I have some target prediction in mind, some target output y plus, and the model initially predicts something else, what changes in the input space x are necessary to move from the original prediction that's different from y plus to y plus. So this equation essentially summarizes most, if not all, of counterfactual explanations. And the visualization shows what's essentially happening under the hood. We're just moving, in the classification case, across the decision boundary, and the changes in the input space are essentially our explanation for why a certain prediction was made or wasn't made. And as you can already see, this particular counterfactual here, it does move us across the decision boundary, but we're still very far away from training samples actually observed in the target domain. And this is just a consequence of how decision boundaries work. You can move across it in different spaces. So it doesn't necessarily mean this is a good explanation, an explanation that a researcher or practitioner is happy with, but it's valid. So the model makes its decisions in that way. So this begs a question that plagued me or kept me entertained during my PhD. Are we dealing with explanations or adversarial examples? So for those of you familiar with adversarial examples, this slide will look very familiar because they're generated in a very similar way. And to illustrate this dilemma or this problem in the context of counterfactual explanations, I show you here different counterfactual explanations using different approaches. So we have a simple model trained for image classification on this famous, very simple data set, MNIST. And in this case, I'm trying to generate for an original factual instance of a 9 that the model correctly predicts. I'm trying to understand what changes are necessary for the model to, instead of predicting a 9, to predict a 7. Now, all of these counterfactuals that you see here, using different counterfactual generators, they all lead to fairly confident predictions by the model that this is now a 7. But of course, if you look at Wachter and Schut, any human observer would not be fooled or led to believe that the new input is actually a 7, which in my mind tells us something about the model that we maybe want to know. But there's been a paradigm especially in the context of counterfactual explanations, that our goal should be to generate plausible explanations, such as the one produced here by this counterfactual generator called Revise. This one does look most like a 7, so it's the most pleasing explanation. It seems to me now, okay, the model is making decisions based on plausible patterns in the data that I would also use to explain this simple classification problem. But the issue with this approach is that these other explanations are still valid. So we essentially have many different explanations for our black box model to explain its predictions. And the question is, which one is the most relevant? Now, the authors behind Revise, this was at this point many years ago, they came up with this very interesting solution that uses under the hood a surrogate model that learns the data generating process, and then the counterfactual generation actually happens within the bounds of that surrogate model. But the question I ask myself in that context is, are we explaining the black box model that we're trying to explain, or are we explaining qualities of the surrogate model. So that led to this paper, which we had at Triple AI 2 years ago, where we essentially argued, no, we need to generate explanations, counterfactuals that faithfully explain the model to really generate a sense of trust in black box models. I want my explanations, my counterfactuals, to reflect properties about the model. So we used some ideas from energy-based modeling and came up with this approach that allowed us to, we think, distinguish between more trustworthy and less trustworthy models. So here in figure 2, you see in panel A a very simple model, so that's the same one as before, a multi-layer perceptron. It seems to me that using our approach, you can see there's certain vulnerabilities. Again, here we have the adversarial example parallel. And then we go ahead essentially and just use techniques during training to make the models more robust to adversarial examples, to have a better sense of their own predictive uncertainty. We combine different training ideas, and we can see how the quality of faithful explanations improves. And this really gives us a signal, okay, I want to trust the model in panel D more in this particular context than the model in panel A. And now, finally, coming around to actually the topic of this talk and the package. We now use in this work the faithful counterfactual generator to essentially present models with their own faithful explanations during training. So on the fly, during every iteration, we say, look, this is a faithful explanation, a faithful counterfactual for your current decision-making, your current predictions, and they look ideally very close to what we observe in the data. So ideally, the counterfactuals that we observe are close to, I showed you that chart with the 2 clusters, they should be close to data that's ground truth data that's actually in the target domain. And then we just, during training in each epoch, we essentially penalize the distance between what we define as plausible explanations and the faithful explanations that are currently generated for the model. And by backpropagating through all of this, we have a hybrid objective. We're minimizing our discriminative objective to predict, to make good predictions, but we're also penalizing implausible explanations. So we're steering the model, inducing the model to learn to make good predictions based on plausible explanations. And we find that this improves post-hoc explainability in the sense that if we then go ahead and post-training generate faithful counterfactuals, they will look more plausible. It also allows us to impose or teach the model about real-world constraints. So to give you one example, one that's actually mentioned a lot in this context is loan applications and creditworthiness prediction. A bank might use a black box model to try and decide whether you should get a loan or not. But there are certain characteristics about yourself that you simply cannot, in practice, change, such as your age. So if age is a factor that goes into that black box model, we can essentially, through counterfactual training, say this variable you should not be so sensitive to. And a bonus of all of this, or perhaps kind of an inherent consequence of the similarities between counterfactual explanations and adversarial examples, is that we also get better adversarial robustness for our models. Yeah, and exactly. So this was actually what I was explaining right now. We start here in panel A with a conventionally trained model. Then we generate faithful counterfactuals. They cross the decision boundary. They're valid, but they look very different from ground truth individuals. In panel B, we impose no actionability constraints. So age here is mutable, but we use counterfactual training, and we can see that the faithful explanations look a lot more, well, they overlap with a set of ground truth individuals. Panel C again, conventionally trained model. This time we impose a mutability constraint on age. So we say that in practice, individuals cannot change their age. The explanations, again, they are valid, but they move into an entirely different part of the domain. In panel D, we can see that the decision boundary has shifted in favor of the mutable feature. So the model is now more sensitive to that variable that individuals can change, det, making it easier for individuals to cross the decision boundary by changing that feature that they actually have power over. And it's essentially not sensitive at all to the age variable. And we have a little proof for this for linear models, and empirically show that this also holds for nonlinear models. So the results here shown with MNIST data again, we see that in the top row here, again, a simple MLP, conventionally trained, counterfactuals in all classes. They don't really look plausible. And then we go to our model trained with counterfactual training, and the counterfactuals, faithful counterfactuals, look a lot more plausible. Should mention here that this is a very small multi-layer perceptron. I have an example later with something a little bit bigger. And here we can see that adversarial robustness also improves. So this was the research part of the talk. Now coming to what we're all here for. So all of this was powered by the Tiger ecosystem. And it is now, as of 2 hours ago, registered, counterfactual training.jl. It's a very simple API, currently tailored towards the FluxML deep learning ecosystem. Essentially, the main ingredients, at least for the to enjoy the whole capabilities that counterfactual explanations gives us, is these 3 packages, so counterfactual training, counterfactual explanations, and Flux, where in the main API call, counterfactual training, the objective is something that comes from the counterfactual training package. The model is just any Flux JL deep learning model that you can think of. The generator, at least in the original version, that branch survives, is any counterfactual generator coming from counterfactual explanations that is also differentiable with respect to inputs. Then we have a training data set. There's an additional input arguments here for validation data set, etc. And then we have just a standard optimizer. That's really, in terms of the main public API, all it is. Now this, much like all of my packages, this was developed for research paper. And here the defining feature was that we were looking at many small models, and our goal was to generate many counterfactuals, also at the evaluation stage, to properly benchmark our models and our techniques. So the focus here was on parallelizing this. So under the hood, counterfactual explanations uses MPI.jl to allow us to multi-process this counterfactual generation stage. And that was used in the original research branch. So for all the results that you just saw for the paper, we used this. So we essentially have a parallel loop that runs on many CPUs, where for each epoch, we first generate a batch of counterfactuals through multiprocessing, and then we backpropagate through that objective, that hybrid objective that I showed you earlier, where the counterfactuals enter again at this second stage here. Now this was great for many reasons. At least in the research context, we could test out different counterfactual generators. So our goal was also to understand what happens if I use the revised generator that I showed you earlier. How does that affect training? Of course, that also means it's bottlenecked by counterfactual explanations .jl performance. The counterfactual explanation structs of that package carry a lot of weight that are useful in the context of inference and explainability, but very much not useful in the context of training. That route was still, at the time, a great alternative and still is for the GPU poor of us. I'm still one of those, you can train models very well on CPUs here as well, but of course it means you're bound to smaller models. Right, and moving on. I know that at least some people at JuliaCon will be enthusiastic about this. At least I was. I got myself a framework desktop, so there I have a little bit more GPU access now, and use that to play around with the package and essentially develop a GPU branch. This one adds kind of detaches from the counterfactual explanations package and adds a native counterfactual generator that is GPU friendly, and it just overloads that main API method that now uses this custom type here. And I took this to the test with a bigger model that is probably way too big for a data set like MNIST, but it was good for illustrative purposes. We can see here the toll that counterfactual training creates, much like adversarial training creates a toll on computational costs. The case is somewhat worse for counterfactual training because we need to backpropagate or descend further into the target domain than with adversarial examples. So here we have, compared to conventional training, a 10x increase in computational times. That's a price we have to pay. But we can also see that in terms of accuracy, and this was also shown in the paper, the counterfactual training approach is on par with conventional training, but we have this reduction in implausibility in terms of explanations that the model learns, which is the main goal. As I mentioned earlier, Taija was my PhD project, and I have much less time now, unfortunately, to spend working on this. So contributions are very much welcome. There are some listed here. Some of them are more performance focused. Some of them are very much open research questions. So if you're working in the field of explainability, maybe that could be interesting. I'll just leave that here. The slides are on my website. And these are links to the QR codes to the software, to the paper, and also to my homepage where the slides live. And with that, a bit early, but time for questions. Thank you. Jeremy. Yeah, so the question is about whether this also works in the regression context. I showed you classification tasks. My whole PhD revolved around classification tasks. There is a branch in this field that looks at regression problems, so it's definitely feasible. I think the most sort of ad hoc approach is to just binarize whatever your regression problem is. So you have a continuous variable, output variable, and you just map that into binary or some discrete space. But I know it exists. I'm not super familiar with it. It's not a trivial substitution. No. Yeah, so I guess this is about how do we actually assess plausibility during training. So here we borrow ideas from energy-based modeling. We need something that characterizes the distance between explanations that we generate and whatever we define as plausible explanations. But we need that distance measure to also be differentiable with respect to the model, or at least provide us some information about the model parameters. So we cannot just use the Euclidean distance between, as one example, between explanations and plausible explanations. So what we use is energy. So that's just essentially negative logits. Yeah. No. It doesn't. So that's, I think, the crux of Echo, this faithful counterfactual generator, and also this approach. We specifically tried not to use any additional surrogate model that helps us quantify density or whatever, because then we're back into this territory where we got to ask ourselves, are we explaining the model that we're trying to explain, or are we explaining qualities of some surrogate model? So the energy component, the penalty, or the parameters that it sees as the model parameters. So the parameters of the model itself go into that implausibility function, but no additional model. Yeah.
I have one very basic question. Could you show one of those plots again where you basically try to project the one class to its counterfactual? Yeah. That one.
Yeah.
So I'm trying to comprehend what's going on there, because is that a visualization of the counterfactual?
Yeah, it's a lot of things going on in this chart, so I appreciate the question. So the stars here are the counterfactuals, faithful counterfactuals, that we produce post-training. The original scatters here, those are the training points. So that's where the decision boundary comes from. We train a model on some training data, and then we take test samples, so individuals from a holdout set, and we generate faithful counterfactual explanations for those individuals. And those are these that you see here. So this is individuals moving from the blue class to the orange class. So you could think of the orange class here as loan application approved, the blue class being loan rejected. Does that make sense? Or? So in the very the problem that I showed at the start, we have some fitted model parameters after training. Those are represented here by the green line, the decision boundary. So that's what the model decides. And then in this context, after training, we want to understand, okay, how does the model make its decision? So we have that second gradient descent, but with respect to features. So we're moving in the feature space. We're decreasing det, and we're increasing h, and we cross the decision boundary. Yeah. So think about it in the context of the loan example. You're one of these individuals in the blue class originally, so you don't get a loan. So now you actually have a right to an explanation in the EU to try and understand, okay, why was my loan application not successful? So your Y plus that we had in one of the first slides, your target outcome is the orange class, is to get a loan. And now we're asking, okay,
What do I need to do to get a loan?
Yeah, exactly.
But how would you do that once the target class is not binary anymore?
If you have multiple, so this goes back to actually Jeremy's question in some sense. If you have a continuous target variable, multiple classes, well, you still just define one. You can be, I can show you in the package docs, but
For example, you showed the counterfactual for the numbers.
yeah.
Is a counterfactual in that thing or in that domain, like what would you need to see to most likely decide for 7, or is it what would you most likely need to see what would you like to see, speaking to the model, to decide it's not a 7?
Oh, to ask it the other way around. I mean, you could phrase it that way.
Showed when making the 9 to a 7 or something like that.
Mm-hmm.
They're counterfactuals that you presented there.
Yeah.
Was it the question, what does the model need to see to predict the 9?
To predict the 7. So we were starting from, maybe I'll show you with this chart. We start with, the blue one here is the factual. So this is one individual image. They're always local explanations. So this is a 0. And the model correctly classifies this as a 0. And now I'm asking these two different models, well, what changes in the image are necessary for you to predict, no, this is a 1. And this is a 2, this is a 3, this is a 4. So here we have your multi-class case, right? We start from the same individual and we're asking for every other output class, what would have been necessary for you to predict that target class. And the point of this illustration is that if I take a conventionally trained model, this has in the top row, this is a simple MLP, but it will get you close to perfect accuracy, predictive accuracy. But once you look at these faithful counterfactuals, you realize, okay, it's picking up associations in the data that helps it achieve high accuracy, but the explanations are not plausible. Yeah, no worries. Okay, yeah, question in the back? Yeah, so there's also an interesting question. You, of course, don't always have a clear decision boundary like this one, where you have two domains clearly separated from each other. You might have class A here in the domain, class B, and then class A again. There's a lot of interesting work in this space. In principle, the techniques work the same way. If you look at the first objective here, we are minimizing some regularization term. And one of, actually the seminal paper introducing counterfactual explanations said, we're just going to make that the distance between your original factual starting point and whatever class you want to end up in. The intuition being that this was presented in the context of the loan example, for example. You want to make individuals exert as little effort as possible to achieve the target outcome. So in your example, if there's different parts of the domain that are populated by clusters of the target domain, then if I choose a strong distance penalty here, my counterfactual will be guided towards the closest available target domain. Yeah, no worries. Yeah? Of course.
Did you ever think about not presenting one counterfactual, but rather a distribution of likely counterfactuals for one of those in the
Yep.
example 8 cases?
Yeah. Yeah, this is another really good question. So the question is about, doesn't it make sense to present a menu of counterfactuals as opposed to just one? There's a lot of interesting work on this, probably the most popular one, already a few years old by some people from Microsoft called DICE, Diverse Counterfactual Explanations. Here the idea is exactly this, that if we go back to the loan example, you might want to present individuals with a menu of choices, and you probably want that menu to be as diverse as possible. So you have very different options to choose from. The DICE approach uses under the hood, it's part of counterfactual explanations actually, we have it in the package, a penalty that ensures that counterfactuals drift into the target domain and then disperse. So those methods exist. They're in the package. Yeah. No worries. Lots of good questions. Thank you. But I think that was the last one. All right. Well, feel free to come and grab me. I'll be around this afternoon. Unfortunately, I have to go home later today, but happy to chat. Thank you very much.
Does anyone know whether we have a session chair here today? Because otherwise I would suggest that we simply start. I think we should simply start. Okay. Yeah, thanks. Yeah, I think we just start if it's fine for everyone. So thanks for being here. Despite there is a little incentive to listen to the talks in the air-conditioned rooms, so highly appreciate that. So this talk is named Handle Your Handles, and it sort of implies that I possibly should explain what handles are. So I think this is the most important question we need to answer first. And luckily, there is a very simple answer to that one. And there is also a bit of a more complicated answer. But with this answer, I passed my PhD examinations, and therefore it can't be too bad. Although I added a bit more to it afterwards, and I probably should do that here too. So the thing is, everyone seems to understand something differently when they talk about handles. So, for example, on a typical Unix system, we have file handles, which are some kind of numerical identifier for an open file. My favorite one is in MATLAB. With their old graphic systems, you had these file handles, and they decided to use float64 for identifying their plots, probably because they know their math and that they learned that float64 has mostly rational numbers, and rational numbers they learned are countable, and therefore why not number your plots with those? So I don't know. So we will just. I'll just show you what I mean with handles on the way during this talk, basically, so we don't need a specific definition. But first, let's check how can we access things. So we are maximally abstract here. So we have the value-based access. You all know that basically just use an immutable type. Node access it. Fine and good. I mean, everyone knows that. Then, if you look at C and the like, next thing which came were pointers. So basically, you point to the memory address where the thing is, with all the problems they come with. And then there came references, which tried to solve these problems. C++, Java, whatever. But we also have them in Julia. And because Julia is cool, we don't only have one kind of reference, but we have two kinds of references. And before we come to the first block, where you probably have no idea what that could be, let's check the references first, because we need that. So for the mutable type, you'll see it there, basically just an example here with an x and y, float 64. And that's it. You have a reference to that, because each mutable type is automatically also a reference on that object. That's the implicit case, and we also have the explicit case, where you really use the ref constructor, which is a huge trap, because ref is an abstract class creating a ref value. And then you can use the square brackets to basically dereference the reference to get the object itself. You can also see it in the sizes, that if you are really talking about the objects, you have obviously 16 bytes per object, therefore 1,600 bytes overall, whereas for the references, for the implicit references, for the mutable ones, only the reference, the pointers basically, are counted. Okay, so what's the motivation for having handles? So we want to have safe array indexing. Don't know whether you have ever had such an example. So you have some edges, you have some nodes, you have an edge index, you have a node index, and then you use your edges and give it a node index, and boom, doesn't work. So I can definitely say, been there, done that. And it's not so fun if you add that to safety critical software. It's also not so fun if you use a programming language which doesn't do bound checking. And it's even less fun if you do it in a way that the reviewer doesn't catch it. I mean, I'm just talking about a friend here, obviously. You're really lucky in these situations that you have your tests, but ideally, it shouldn't happen to begin with. And the thing is, the get index, when you have a vector of edge and you add a node index, that is just not a valid combination. That's not a combination you ever want to have. And what do you do when you want to avoid combinations? You use the type system, and the type system basically can make the node index a special type. Let's call it node index with uppercase. And then we have the get index with the new signature, basically, should be a colon. And that is exactly what handle.jl does. Michael Ewert is the author there. And so let's just rename node index to node handle to be consistent with what we already have in Julia. So no surprise here. Last thing is the handle, and the idea is a pointer or reference answers where is something, whereas a handle answers which one do you want to have, which in the end obviously also ends up in somewhere, but it has a different starting point. Okay, so let's look at the progress. We started with a reference to a value, so that was quite comfortable. And it wasn't too bad in terms of memory. I mean, you have that reference. In terms of performance, you just need to access that memory location. So you need to access one memory location. So now we have this fancy handle thing, and afterwards we now need two things. We need the index we want to go to, but we also need the array where the index is valid for, basically. So now we have two things, which is less comfortable, thinking about moving two things around through your program via the stack, for example. And we have this interesting accessing pattern here for memory. Everyone who programs C or something like that knows that by heart. Basically, you need to go at the start of your array, and then you need to move n times or e times the size of the object in memory. And as Julia starts with 1, you also get the -1 here. So basically, safety went up, and everything else went down. So maybe not the best progress overall. So what can we do about that? So let's start with comfort and memory. So instead of handing over the two things separately, what do we do as programmers? We just create struct, two fields, put them in basically. And now we can move them over. We can give some methods to that type, make it more comfortably. Works in principle, however, there's an even better solution, and that also improves your memory, because you don't need to store the same array reference in all objects of that type. You can simply store it somehow in the type, whatever that means, but it's obviously type related and not object related. So where do we end up with that? Safety is still a plus. Comfort and memory, kind of a wash, not really better, not really worse, maybe a bit worse, but not a lot. Performance, still not really great. Okay, so let's look at performance. Computers evolved over time. So don't know how many people are in the room who really have programmed on 16-bit computers, but they actually were a thing. I think most of you have at least seen 32-bit computers. Nowadays, standard, obviously, 64 bits. And with that, the pointers grew. And And it's interesting what that implies, because every reference, every pointer obviously grew, but the reason you had this larger address space was mostly that you only want to address the whole memory, basically. And the number of elements which you can address have also increased enormously. And maybe you don't need all these objects all the time. So let the user specify the index type. If the index type is specified by the user, it can be selected as large as needed. And if all our indices now need less memory, we obviously have a plus on memory. Also, memory accesses evolved, so we have this whole caching hierarchy, and we have cache lines. So if you access some memory, then you get a bunch of memory, 64 bytes typically. And the thing is, CPUs got faster than memory got faster. So CPUs are often waiting for memory. There is something like memory locality. There are two flavors. We have the temporal thing. So if you had something once, you probably will have it soon again. Or if you had once, you probably have something in the neighborhood again. This is the spatial locality. And now if you allocate one mutable object after the other, they can be distributed all over the whole memory, basically, which you see here in the top row, basically. And if you allocate them all in one array, then they are all located next to each other. So if you access one of those, you automatically get a lot of objects close to it in your cache line, and chances are you will need them, and then you have a cache hit instead of a cache miss, and you will save quite some time. Then there is bounds checking. I mean, now we have the array and the handle, the index, bound to each other. That means if it was in bounds once and you don't shrink it, it will always be in bounds because you only use those two together. You can't use this index on a completely separate array now, which might be smaller and therefore out of bounds. So that's quite nice. So you can just check it once and you're done forever for that, basically, and you are still provably safe. So that's especially nice if you do some real-time programming, because then you can do the checks before you start your real-time phase. Accesses are also not so bad because people know their job, so that is quite fast. And although you have an additional memory access, there are only two cases. Either the accesses are rare, then they don't matter, or they are frequent, then your arrow pointer is always in the cache, and therefore it's also okay. So overall, lots of improvements. Finally, everywhere thumb up. COM4 is still a wash, but we can live with that. And if you look at benchmark results, you get some improvements by just using handles compared to the standard approach. Obviously, that's kind of a best case scenario. Typically, you have a mix, but 1.7x is still not bad. I've added an example, basically, so you can see how that looks like. A very similar syntax, just creating the handle and dereferencing it again with the square brackets. So we are safer, we are smaller, we are faster. And I think that's something quite remarkable. So I would hope that that pattern is used more often than it currently is. And I'm sorry, I still don't know what handles are, but at least I now know it more efficiently. So thanks, everyone.
Question from the audience. Thank you for the delightful talk.
Today, I would like to present you what we've did the last 4 years, namely developing RESI, which is a simulation engine for sector-coupled energy system simulation on a scale of buildings and districts based on a novel approach. Okay, but what does it actually mean? Let's dissect it. We start with energy system simulation. Unfortunately, don't have the time to go into too much detail what this is. I hope it becomes apparent throughout this talk, if you don't know already. But it is a common form of analysis in the field. And RESI exists in the context of hundreds of similar tools. They're not all the same. That would be kind of weird, but they are similar enough to count. So we have this huge repository of existing tools, and now there's another one. I'm coming back to why that is. And sector coupled is a fairly German term, which basically just means that we're regarding different kinds of energy carriers like heat, electricity, hydrogen, etc. Simulation stands in contrast to optimization, which is also a common form of analysis in the field and perhaps the dominant approach, especially if large energy systems are concerned. And engine in this context means that the software we develop expects the input or the required input data as data files, and there's no coding necessary to run it. So it's an engine, it just needs fuel, so to speak, and then spits out results. And the scale of buildings and districts means that different considerations and assumptions have to be done, have to be made, and which also affect then which tools are suitable for the task at hand. And district, unfortunately, it doesn't have a hard definition, but usually it means up to hundreds, maybe low thousands number of buildings, and which are mostly residential with some commercial or industry smattered in. Okay, so I said the dominant approach in the field is linear optimization and mixed integer linear programming, and RESI is different. So that's what I'm presenting here today. And if we try to classify all these tools that exist on the basis of the scale they regard and the amount of details they consider, there are basically 3 different use cases that we could use to classify tools. One is regarding the national and international energy systems regarding whole countries. And next lower on the scale, but also with more details, is municipal development plans, and then lower on the scale again, and finally with the maximum amount of detail are individual construction projects where at the end of a project you have something actually built that exists in reality. And in reality that means you have no optimal control because the plants and the systems they actually built that need to be programmed with rule-based control, because there is no optimal control in reality. And you also have no perfect foresight. Just consider a weather report, it's accurate to maybe 3 days. You have state-based control, where one component is controlled based on the state of another component, and just a whole number of non-linear effects. So that's in reality. And what we aim with RESI is that in the beginning of a construction project, there are some key decisions to be made, and these are carried forward throughout the entire project up until the building is realized. And we hope to aim, or we aim that to support this workflow where these key decisions are carried forward. But it also means that in real operation, we need to consider these things that we don't have in model land, where everything is nice. Okay, so let's get a bit into how it works. Let's consider a very simple energy system where we have a heating demand, a gas boiler that supplies this heating demand, and then access to a public gas grid which supplies the fuel for the gas boiler. And in the standard approach, you would take this energy system and the limitations that exist around it. For example, the specific heat demand is to be supplied in any time step, or rather you are working with time series. So you have the whole time series of the demand as input, and some other considerations, and you turn this into a set of equations, and there are a whole number of iterative solvers that can solve these equations and then fill out the blanks which you actually want to know. And we are following a different method, which is based on a fixed calculation order, where in this case, first the demand says, okay, I need this amount of energy. Then the grid says, okay, I can supply up to this amount of energy. Then third, the boiler can say, okay, based on these two considerations, I can calculate how much gas I need to supply this demand. And finally, the grid can say, okay, the amount of gas you need is less than I can maximally supply, so it's fine. But now this in turn incurs the problem, how we determine this order of operations. And this is really the crux of the whole approach. What I said earlier, where the boiler calculates its own state, this is something we can kind of modular put together with a component model. But if you're watching the whole energy system, this order of operations then has to determine that it works, basically, so that everything sums up. And we start with a base order, which is informed by a categorization of components based on one of 7 categories. First, we have fixed sources and sinks, which basically supply or request a certain amount of energy, which is fixed within a time step. Then we have buses, which is a special type of component, which is necessary whenever you have more than one component supplying more than one other component. And transformers, which are basically any component that transforms from one form of energy to another, which is kind of in the interior of the energy system, where the sources and sinks are the exterior, where the system boundary sits. Then there's, of course, also storage, which have an internal state. And finally, flexible sources and sinks, which can supply up to some maximum amount of energy within one time step. So that's the 7 categories of the components, and there are 4 essential operation steps. First is control, which basically says this component calculates its internal control mechanisms based on the state of the whole energy system of the last time step. Then there's process, which essentially means, okay, you now supply or demand or distribute or transform energy. And transformers in particular have another step, which is potential, which is kind of similar to the process step, except it only considers how much possible energy other components can supply, basically as a limit approach. And finally, the storages, as they have an internal state, have 2 separate steps, one for supplying energy and one for taking in energy. Okay, so this is the space order here displayed with some arrows, but this is unfortunately not enough to solve this problem. There are other considerations to be made, and one such is how energy is distributed on a bus. And what is shown here is very simplified from what the actual algorithm is, but essentially buses have like an internal data structure which kind of looks like a table where information is kept of which input supplies how much energy at which temperature, if heat is concerned, to which other output. And this internal data structure is then updated every time one of the connected components on that bus updates its own state, or rather calculates how much energy it can supply or take in. And this algorithm gets particularly complicated when there are multiple transformers on a bus, also if these are connected with other transformers or other buses in like chains, which we see here. This is admittedly a bit of a unrealistic scenario. You wouldn't typically build it like this, but suppose you have it. You have a whole bunch of transformers and various buses that communicate these energies across these chains. And essentially, if you have a chain that starts on the left, goes all the way to the right, and all these components need to communicate how much energy they can supply, but it also depends on all other components. So how does this work? It works by, again, categorizing the components, but this time by their position and the connections they have within the energy flow network. There are like terms here, like a middle transformer, which means there are transformers to the left of it, so to speak, and others to the right. Or there's a middle bus, which again says there's something on the left side and something on the right side, and middle parallel branches. You don't need to remember these, but there's a bunch of categorizations. And the algorithm then uses this to determine the actually final potential and process steps, in which order they need to happen for all these transformers to work correctly. And the kind of amazing part is that in such a complicated system, each transformer only needs one potential and one process step, but the actual algorithm jumps around, basically. And another problem I now have is trying to explain how this works exactly, this famous algorithm as it works. The problem is we only have the code. We don't have a mathematical formulation for it. We tried, but we didn't come up with anything. We are fairly confident it works in most cases that we consider relevant, although we know some edge cases where some manual intervention into this order of operation is necessary, but they are edge cases in the sense that they shouldn't happen in typical NEC systems, although you might run into these. So we're trying to keep a list of edge cases where we know problems could arise. So if there's something interesting for you and if you like a challenge, you are welcome to contribute, and maybe we can find a mathematical formulation for this problem where our code then is the solution to at least a weaker form of the problem. I'm sure there's a paper somewhere in there. Okay, so another thing to be said is this algorithm runs at the beginning of the simulation, and it takes some significant amount of time. Like for medium to large size energy systems you're simulating, it can take several seconds to calculate, which, given the speed of Julia, is significant. Okay, but for the individual components, we have models implemented on various levels of details. There's too much to list them all here, so just picked one example. For example, a ground-coupled seasonal thermal energy storage, also known as a pit storage, where there's a big pit with water inside that's heated up. This is modeled by a one-dimensional n-layer PDE within the storage, where you have calculated ambient losses to the surrounding, like the ground and the air, and within the layers, diffusive and convective heat transfer. And this is coupled to a ground simulation, which uses a finite volume scheme, which is two-dimensional, like pictured in the picture on the right, with rotational symmetry, because typically these kind of pits are rotationally symmetric. It would be a bit weird if they were not. But this is a component model which calculates the amount of energy this single component communicates, but it uses the overall simulation framework to then communicate with other components the amount of energy this is transferred and at which temperatures. Or there are some considerations for special interactions to be had where additional control modules are necessary, but again, these are fairly specific edge cases. Okay, one key thing I said in the beginning was nonlinear, or the operation in reality is often nonlinear, and based on rule-based control, which we can model with our system. For example, here we have a heat pump, which is connected to a storage, and the actually heat demand is auto supply on a bus. So now there are things to consider. For example, the heat pump should only operate with a high share of renewables in the power grid. It should work on hysteresis based on also known as a bang-bang control on the heat storage. And the COP of the heat pump itself has also various effects that mean that its operation is highly non-linear. And some of these control schemes are neatly packaged into modular attachments that you can attach two components, also multiple modules to one or to every component. One of these modules, with the caveat that these control schemes have to be implemented as code. These are not part of the input file. Although you can, of course, parameterize them in the input file. We've also considered possible extensions of these control schemes. For example, modeling model predictive control within the simulation using the simulation itself. So basically calculating into the future, then communicating backwards in time to an earlier time step. And co-simulation with other simulation tools is also something we're looking into, because these component models are kind of, not really, but kind of already co-simulations with other simulation models. The outputs that the engine calculates also include economic results and emissions based on a fairly simple method on a German standard. The results are annuities, presence values, and cash flows on the economic side, and on the emission side, the emissions that are incurred through the processing of energy, and can optionally also include embodied emissions. But it has to be said that garbage in, garbage out definitely applies here. So the quality of the result is mostly driven by the input data. I said earlier, this is a simulation, not an optimization. And unfortunately, the methodology only allows for black box optimization, but we have implemented this, and it works fairly well, I must say. We're quite proud of it. It offers various algorithms for black box optimization from packages Optim, black box Optim, meta heuristics, NLOpt, and Nomad. So you have a whole range variety to choose from. And because the simulation itself is necessarily single-threaded, we can leverage multi-threading to run multiple simulations in parallel. Any set of parameters can be optimized, but not the energy system topology itself, except when one component is sized down to 0, so it's effectively removed from the system. We've also implemented sensitivity analysis on a global scale, within a parameter space, based on a surrogate model using polynomial chaos expansion, where the results of a whole bunch of simulations that you already run for optimization are then fed into the to fit the surrogate model to the results. And from this surrogate model, then we determine Sobol indices for the individual and the interactional contributions for each parameter. And there's also possible to do local sensitivity based on a specific parameter set. The outputs are a bunch of pretty pictures, which are very useful for fast iterations of this workflow, but the plots itself are often already enough to do the analysis you want to do. And outputs include time series data on almost all component-specific outputs, and also the energy flows across buses, like how much energy supplied this input to this output. When we started development, 2 out of the 3 main developers behind it had little formal education in computer science and/or programming. I was the one with the experience, but the other 2 started getting into coding with Julia fairly quickly, so that was very positive. However, the REPL was an unfamiliar concept to all 3, and its usage is still mixed within the team. Like, we do use it sometimes for some things, but it doesn't quite, it's at odds with our experience based on other projects and languages. But I also must say, Resi is perhaps an unusual package for the Julia ecosystem, and not all of these lessons that we learned necessarily apply generally. Sorry. One thing was also the submodule structure, or where you place code and how. This is, to be fair, not a problem specific to Julia, but it is one that occurred, and we still don't have a good solution. So for example, on the left you see the main module file, and there's one included submodule file, which is responsible for 3/4 of all files in a project and 2/3 of lines. So It's a huge submodule. And then we have also other included files which are not submodules, but large enough to justify it. But the interdependencies make it kind of tricky to do that, really. Another thing was that from our experience, but also the model itself lends itself well to object-oriented programming, which, well, doesn't exist in Julia. And we're kind of missing common features such as classes, inheritance, on structs, etc. Well, structs are basically classes. But through some compromises and multiple dispatch, we did find a workable solution. And finally, debugging is extremely important if you're developing simulations, because the code might run incomplete, but it's still the wrong result, and you need to figure out how. And for this, important features are breakpoints with conditions, stepping functions, and a quick view into the state of variables. And fortunately, the Julia for VS Code extension offers all these, so that's great. And at this point, a shout out to the developers of the extension and debugger.jl, because they did great work. Unfortunately, we ran into very frustrating problems with it, which delayed development quite a bit. So I hope I interest you in our work, so feel free to check it out, and I'm open for questions.
Questions from the audience?
Hello, thank you for the presentation. In your optimization, what do you put as objective function?
It's up to the user, essentially. Let's go back here. Typically, you would use economic results and emissions, but you can, in theory, pick any simulation output and use it as part of the objective function. Although most of the algorithms from these various packages, they require a single objective to work properly. And in this case, you need to do factored linearization of the output. So for example, if you pick the unmet demand as one of the objective functions that needs to be minimized, you can use it, but if at the same time you want to also minimize the costs, which you essentially always want to do, then you need to figure out a good linearization of these two objectives into one.
Yes, because I would expect if you do cost, then there will be cases your energy will not be met. So you will have...
yeah, that's actually a good point. I think maybe I forgot to mention it, or maybe it was one of the slides I cut out. But the overall energy balance of the entire systems is not necessarily upheld, because unmet demands is an important output of the simulation we want to know. And for optimization, this is also especially important, because these unmet demands are then penalized heavily, and which then leads to the optimization finding sizing. If you do a sizing optimization that works barely, it's like just barely large enough the components to work properly. And as soon as it gets a bit smaller, then the penalties kick in and the optimization figures that out. Yeah.
Thank you from me as well. So the question connects with the previous point. So with the unmet demand and the lack of energy balance. So you infer the lack of the unmet demand by the decrease or increase of energy in the system, or is that somehow explicitly?
No, it's rather usually unmet demands happen when, well, demand with our fixed calculation order, the demand says I need this amount of energy, which is then subtracted, so to speak, from the system. And then the transformer responsible for supplying this amount determines, but I can't supply that much energy, so I'm just going to my own maximum. And the difference is then the unmet demand.
But that is tracked?
Yeah, it's tracked. It's a simulation output.
Right. Thank you.
Yeah, I was just wondering if you were looking into libraries such as Modeling Toolkit for building such a simulation, and why you didn't choose to use it in the end.
It's a bit of a good question. Again, it started 4 years ago. It could be that at the time we looked at it, I can't quite perfectly remember, but we looked at various frameworks, but found that none of the frameworks, at least at the time, with our research at the time, fit the bill quite. like we needed to. And so essentially we started completely from scratch. It's possible that maybe we could now use one of the frameworks or libraries to re-implement it, but we definitely don't have the time to do it.
I'm not quite sure if I missed it, but how do you validate these models? How do you know that it works correctly or predicts correctly? You can't implement a district or simulate, well, do an experiment, right?
We can, actually. It's kind of. It's a bit tricky. So it's not like a particular valid. We have some actual measurement data, which we did use to mainly validate the individual component models, because there are more data available. But we're also looking at modeling entire energy systems, like for a district. And we have some data where we're trying to validate, and it's looking good so far. But of course, this is then only one use case, and with more data we could do more validations. But this is also not easily done. It's like multiple days of work just to wrangle all the data, make nice time series out of it, then feed it into it, model, then figure out what went wrong. Because the problem in a built environment is the measurement data is dirty. You need a lot of cleanup to make something out of it.
Okay, yep, thank you.
Let us thank the speaker again. Is our next speaker here? I am not the speaker chair. I'm just here. Is this the last one? Amazing. Thank you so much.